Welcome, everyone, to the Monetary Economics meeting of the 2026 Summer Institute. My name is John Steinson. I'm a program director of Monetary Economics, along with Emmy, sitting over there. Before I hand it over to the first speaker of the day, I just have a few little housekeeping things to say. First, I want to remind everybody of the NBER's Code of Conduct, which you can find on the program. Second, I want to remind everybody that we're live streamed, and ideally speakers actually speak from the podium because there's a camera here so the live stream people can see. And ideally people that ask questions, I mean, we're not going to be 100% about this, but there are mics around, and ideally the questions are asked from the mic. The format of the meeting is that there are 45 minutes for each paper, and they're going to be kind of light questions throughout. And then hopefully the speakers can end a few minutes early, like 5 minutes early. And so we can have some questions at the end as well. Okay, so that's it. Our first speaker is Jordi Gali.
Good. Well, good afternoon. Thanks so much for including the paper in the program. So just to give you some background, this is what I will present is like a second lecture in a series of lectures sponsored by the Econometric Society and named after Lucas and Modigliani, and under the general title "Rethinking the New Keynesian Model." So in case you're curious, on my website you can find the slides for the other two lectures. And this is very much inspired by a paper that I had the opportunity to discuss at Jackson Hole last summer by Emmy, John, and Venance Riplier, I think, is a student at Berkeley, titled "Beyond the Taylor Rule." So motivation for this, so as we know, you all know in this audience, the monetary policy rule is a key element of the new Keynesian model. A conventional assumption made by widespread used models is that rule takes the form of a rule for the short-term nominal rate, and usually it's some sort of a Taylor type rule. Also, a Taylor rule has often been used as a benchmark for the evaluation of monetary policies, and this is potentially misleading, and this is one of the messages that was in the paper, the Nakamura, Ripley, and Steinson paper, which I will refer from now on to as NRS, okay, because I will refer to it several times. So what I do here is to propose an alternative, both for modeling and for evaluation of monetary policy, which is based on long-term real interest rates, a rule for long-term real interest rates instead of a rule for short-term nominal rates. So the outline of the talk is straightforward. First, I will review the basic idea that using Taylor-type rules for the evaluation of monetary policies may be misleading, and then I'll make the case for long-term real interest rate rules, and then I'll show you some real-world examples to illustrate that case. I will conclude. So related literature, well, obviously is the key Taylor reference. Then there are many papers that have used Taylor-type rules for the assessment of monetary policy, both academic papers and also in central bank practice. This presentation is also related to indeterminacy and the Taylor principle. Here I list some papers from early papers to more recent papers. And then there are, this is also related to proposals for alternative rules. In particular, a number of people have proposed and used rules for the short-term real rate as opposed to the short-term nominal rate. Here are some references. And there's at least one paper I know of in which a proposal is made for using rules for the long-term nominal rate. So here, I'll try to make the case that this falls short of having some of the desirable features. That's why I'm calling for using a rule for the long-term real rate. Okay, everyone knows here the original Taylor rule, obviously. And so this is the picture from Taylor's original paper, possibly one of the most famous pictures in macroeconomics, in the history of macroeconomics. And as you know, Taylor proposed his rule as a description of monetary policy in a specific period, the early Greenspan years. And so this was viewed at that time as a realistic description, and hence it was embedded. It was kind of natural to embed in new Keynesian models, for instance, in which monetary policy rules matter, a rule that had a similar specification. So that's what we could call a Taylor type rule, like the one you see here on the screen. Now, originally, the Taylor rule had a positive dimension. It was meant to be descriptive, but of course, the period in which it applied was also a very special period, what we now call the Great Moderation, in which the performance, the macro performance of the U.S. economy was viewed as being very good. So with stable inflation and stable output, mild recessions, and so on. So the Taylor rule evolved as having also a normative dimension or interpretation. It was kind of a benchmark of how monetary policy should be conducted. And a number of papers, in particular papers by Taylor himself, or also others, used it as a benchmark. Now, there's one particular aspect of the Taylor rule that was important from that point of view, which is when embedded in a new Keynesian model, some other model, it's the properties that it had to satisfy it in order to guarantee a unique equilibrium. And in the basic new Keynesian model, that property is the one that you see. The condition for a unique equilibrium is the one that you see here. So the response of the central bank to inflation and output should be sufficiently strong. Now, beta is the discount factor, kappa is the coefficient on the output gap in the new Keynesian Phillips curve. Now, 1 minus beta is likely to be small. So what really matters is phi pi here. Okay, so we can, for much of my talk, I will just simplify this notion of the Taylor principle as the inflation coefficient being larger than 1. Very good. So, so to what extent, so U.S. monetary policy has followed something close to a Taylor rule, and to what extent has it satisfied the Taylor principle? Well, so let's look at a picture from the NRS paper that updates the famous Taylor picture. This doesn't seem to, oh, here we go. Okay. So here you have the original Taylor rule, but update and the federal funds rate updated up to 2025 or something like that. And the shaded area is the original Taylor sample. So what you can see is that in recent years and over the past 2 decades, the deviations have been very large. And if you see specific episodes, for instance, the recent inflation surge, it's not, those deviations have been large, and one may wonder even if the Taylor principle has been satisfied. Very good. So obviously, one simple conclusion from just looking at a picture like this is that monetary policy in the U.S. for the past 2 decades or so may not have been good monetary policy. Okay, because it deviates so much from the Taylor rule, and again, many authors have made this point. Taylor himself has been very forceful at making that point. So two observations. First, optimal monetary policy is not always implementable by means of a simple Taylor rule. Okay, so the fact that we don't have something that the actual policy rate doesn't follow a simple Taylor rule doesn't mean necessarily that monetary policy is bad. And optimal monetary policy's observable outcomes, okay, do not always satisfy the Taylor principle, even if the rule that the central bank follows satisfies the Taylor principle. Okay, so again, deviations from the Taylor rule or from the Taylor principle should not be interpreted as prima facie evidence of monetary policy. So I'm going to illustrate this, and here I'll follow pretty much the NRS paper as follows. I'm going to look at, I'm going to consider a simple environment, the basic New Keynesian model, which the central bank behaves optimally, first under discretion, then under commitment. And then we'll look at what an econometrician may conclude by looking at the behavior of interest rates and inflation generated by optimal monetary policy. Okay, so here's the problem. So it's a standard minimization of a discounted sum of a quadratic function of inflation and the output gap. You have the New Keynesian Phillips curve with a cost push shock, which generates a trade-off between stabilization and inflation and the output gap. And then you have a dynamic IS equation with a shock that you can interpret as a discount rate shock or demand shock that can in principle be completely neutralized by monetary policy. Okay. Very good. So let's look at optimal monetary policy. So first, the case of discretion. So this is taken off the shelf from, say, chapter 5 in my textbook. So if you solve the problem of optimal monetary policy when the central bank takes as given expectations of future variables, because it cannot commit to future policies, the equilibrium under that policy is represented by these two equations that you see here for inflation and the output gap. Okay, so the stars here denote equilibrium under the optimal policy. And the interest rate the equilibrium interest rate under that optimal policy can be solved for by using you can be backed out by using the dynamic IS equation, and it looks like the expression you have here. But notice that you can combine this equation with this equation, and you can rewrite the interest rate as a function of inflation. Okay, so this looks like an interest rate rule. So now look at the coefficient in front of inflation. So suppose that this ratio, sigma kappa divided by theta is the weight on the output gap in the loss function of the central bank. Suppose that this was larger than 1. So then the rule that you have here, okay, would implement, then this coefficient on inflation would be larger than 1, and this rule would implement the optimal outcome as a unique equilibrium. Okay, but suppose that the ratio is less than 1. Okay, then we need to somehow fix the rule, and the way we do it is by adding or appending a term here that you see here that responds to deviations of inflation from the desired level of inflation at each point in time, pi t star. Okay, and then if this condition is satisfied, okay, the sum of the coefficients on inflation is larger than 1, and the equilibrium will be unique, and this term will be 0 in equilibrium. So this will indeed be satisfied. Okay. Now, in both cases, the Taylor principle is satisfied, and pi star and y star is implemented as a unique equilibrium. Now, but what is the observed relation? And the observed relation is the one that you see here. Okay. Here on top. Okay. Now consider. Let's put ourselves in the position of an econometrician that observes interest rates and inflation. and estimates a Taylor rule, the simplest version of a Taylor rule. Okay, so what can we say about the estimates that this person would obtain? So first, if that ratio, okay, is less than 1, the estimated Taylor rule will indicate violation of the Taylor principle, even though we know that that's not the case. Secondly, a rule like this will have, in this case, there will be, its credibility may be questionable because, no one will ever observe this response. Okay, this will be an off equilibrium response. Okay, so you can point to this as a limitation of such a rule. Third, the residual from the estimated rule should not be interpreted as an exogenous monetary policy shock. Again, contrary to common practice, the residual from this rule, okay, again, this is optimal monetary policy. Here, the central bank is not in the business of generating instability for its own sake. This is the demand shock in the central bank in order to stabilize the economy, not to destabilize it. It responds 1-for-1 or adjusts the nominal rate 1-for-1 to that monetary policy shock. Now, so there is an alternative that would, in principle, overcome this problem, in particular the first problem, which is the one that we pursued in my paper with Rich, which is here, and Mark Girdler, which is to implement the policy through a forward-looking rule, in which the central bank responds to expected inflation as opposed to current inflation. In that case, the representation takes this form, and this rule, you see the coefficient will always be larger than 1 and will implement the desired outcome as a unique equilibrium, and an econometrician that estimates this rule will actually get a consistent estimate for this, okay, and will not be misled. Okay. In the case of commitment, we know that the optimal policy implies very different properties for inflation. In particular, it implies that the price level is stationary, okay, of a process like this. And one can show it in equilibrium, the nominal rate, okay, again, we can back it out from the dynamic chaos equation, can be shown to take this particular form, okay? So this suggests that, so this will be satisfied in equilibrium. No? The question is how to implement it. And, it would seem natural to implement it through a price level targeting rule, like the one that you see here, okay? And for which the determinacy condition we know is that the coefficient on the price level should be positive, strictly positive. Now, again, let's consider, let's suppose that this coefficient, this ratio is larger than 1, okay? In that case, this rule will implement the equilibrium, the desired outcome as a unique equilibrium. But if this coefficient is less than 1, again, we can use the same trick that we saw earlier in the case of discretion. We can just append a term here that responds to deviations of the price level from the desired path of the price level, and to the extent that this coefficient is sufficiently large that it satisfies this condition, the desired equilibrium, the desired outcome will be implemented as a unique equilibrium. So this PT minus PT star will be 0, and this will obtain, and in the desired, and again, everything will be fine. Now, the observed relation in this case, the relation that our econometrician will observe, is something like this. Now, suppose that the econometrician doesn't know that the central bank follows this complicated optimal policy with commitment, and the econometrician just estimates a Taylor rule, okay? Estimates a Taylor rule like this, and one can show that the OLS coefficient, the OLS estimate converges to this term, and again, the monetary policy cannot be better than this. This is optimal policy with commitment. You cannot improve on that. And still, the econometrician may conclude that that the monetary policy does not even meet the minimum desideratum of guaranteeing a unique equilibrium. Okay, so again, assessment will be misled, okay, to the extent that this is less than 1, which could very well be the case. Okay. Very good. Now let's look at the data. Let's play this game ourselves. Okay, so let's take the US data and let's estimate using OLS this simple Taylor rule. Over the period, starting in 91, I restrict myself to this period because of some data that I will use later, which is restricted to this period. And you see the coefficient on the OLS coefficient, the estimated OLS coefficient on inflation is systematically less than 1, whether you use CPI or core PC. Of course, you may say, oh, we've had these episodes with a binding zero lower bound. It's not surprising, that the central bank has not responded sufficiently strongly to inflation. Okay, let's dummy out those ZLB episodes, which I do here in the second column in each case. And again, the coefficient on inflation remains significantly below 1. Okay, so our econometrician will conclude that during this period, monetary policy in the US has not even satisfied the Taylor principle. Okay, so now let me move on to my to an alternative, the alternative that I propose, which is to focus on the long real rate as opposed to the short term nominal rate. Okay, so just to motivate this, let's think about how monetary policy is transmitted, again, from a theoretical point of view. So if you take, you derive a log linearized consumption function, assuming in this represented infinitely lived representative consumer, this is what you get. Okay, you get consumption is a function of expected output, and it's a function of current and expected real interest rates, and ZT is the preference shock. Okay, RT is the short-term real rate now. And now consider a console that pays a constant real coupon, so that I will take to be like the long-term bond. Okay, so one can show again up to a first order. There's a simple relationship between the yield, the real yield on that console, and the current and expected future values of real rates, and it's given by this relationship. Okay, so you can see now you can combine the two, and you can write down the consumption function as a function to what I will call from now on the long real rate. Okay, so the long real rate is what captures the direct effect of monetary policy on consumption. The central bank has to change one way or another, is to manage to change the long real rate in order to have an effect on consumption. Okay, now let's consider inflation now. In the basic New Keynesian, now we need a model for inflation, so take the basic New Keynesian model. Okay, inflation can be written, if you iterate forward the New Keynesian Phillips curve, as being proportional to a discounted sum of future output and plus terms that will be independent of policy. And output itself is a function of current, if you iterate the dynamic Ayes equation forward, of current and expected future real interest rates. Okay, if you combine both equations, okay, you can derive a simple relationship that you see here between inflation and the long-term real rate. Okay, so the variable in order for the plus terms that are independent of policy. So in order for the central bank to influence inflation today, it must necessarily, through the lens of this model, influence the long-term real rate. The same is true for investment. So let me skip that. This is an example of the Q theory of investment, in which investment also can be shown to depend on the long real rate. So here are some observations. So first, as I said, the long-term real rate is a key determinant of the impact of monetary policy on aggregate demand and inflation. So it is natural, I would argue, to think of policy, monetary policy, in terms of its implications on the long-term real rate. Or put in different words, it's a bit awkward to think of policy without thinking about of its implications on the long-term real rate, given that's what matters. Not to say the only thing that matters, at least through the lens of the simple model. So obviously this includes current and anticipated changes in the policy rate that will affect the long real rate, but also unconventional policy like QE or that aims at changing the term premium. Okay, so the gap between the long rate and the expected future short-term rates. Some discounted some of that short-term rate. So a corollary of this, if you agree on this, is that one may want to describe monetary policy directly as a rule for the long real rate, leaving implementation in the background. Okay. So this is one point. And the second point is that a focus on the long real rate, as opposed to the short-term nominal rate or the policy rate, allows for a better assessment of the adequacy of monetary policy. And so this is what I'm going to illustrate next, just by going through exactly the same exercise that we did earlier using a standard Taylor rule, but now using, let's call it a Taylor rule for the long real rate. Okay, so first, it's very easy to show how to embed a long real a rule for the long real rate in the standard model. So here's take this simple rule. So the long real rate depends, it's a function of inflation. Okay, so you combine it with the other equations of the model, and that yields a difference equation for equilibrium output. Okay, and this difference equation has a unique solution to the extent, you see it probably from here, that this ratio is less than 1, which requires that phi pi is positive. Okay, so that would be the condition for this simple rule to guarantee a unique equilibrium. Okay, and this has a natural interpretation through the lens of the Taylor principle. What you want is that the long-term nominal rate increases more than 1-for-1 relative to long-term inflation expectations. Okay, now let's consider now monetary policy assessment by an econometrician that has this rule as a benchmark. Okay, now, and let's start with optimal policy with discretion. So it can be shown, okay, that the optimal policy with discretion that we have solved for earlier can be implemented by means of this rule for the long-term real rate. Okay, so notice that the inflation coefficient is always positive. Okay, there is no off-equilibrium response required whatsoever, so there are no credibility issues. And an econometrician that estimates this simple rule for the long real rate, okay, will obtain a consistent estimate for this coefficient and will conclude correctly, okay, that in particular that the rule satisfies the Taylor principle because it will obtain a positive coefficient. Okay. Oh, okay. Now let's consider now the optimal policy with commitment. Then this is a bit more less straightforward, but one can show that this rule will implement the outcome of the optimal policy with commitment uniquely. And again, let's consider an econometrician that estimates this equation, this rule for the long-term real rate. Again, it's a misspecified rule, okay? But still, the econometrician goes ahead and obtains an estimate for phi pi that that converges to this object here, and that can be shown for, you know, to the extent that beta is close to 1. This will be positive. Okay, so again, our econometrician, even if the equation that the rule that it estimates is misspecified, it will conclude correctly so, okay, that the central bank follows a rule that satisfies the condition for a unique equilibrium. Okay, so now let's take this to the data. Okay, now we're econometricians ourselves, and we estimate this rule for the long-term real rate. And here, obviously, I don't have something like the counterpart for this real yield on a console, but I'm going to use as a proxy the the 10-year Treasury yield minus the 10-year inflation forecast from the Survey of Professional Forecasters as a proxy for the long-term real rate. Okay, so I estimate that, again, using the same data set as before, and notice that the coefficient on inflation is systematically, no matter what inflation measure I use, whether I dummy out the zero lower bound period or not, a positive, and significantly so. Okay, so there will be no misled evaluation here of, here the econometrician will conclude, okay, in contrast with the previous exercise, using the short-term nominal rate, will conclude that the monetary policy, the US monetary policy, has been conducted in a way that guarantees a unique equilibrium. Okay, so the conclusion is very different. Okay, so I have made this case for focusing on the long-term real rate, and now there are two questions that are natural. Why the long-term real rate? I mean, it would be easier to use maybe the long-term nominal rate, and then we don't have to worry about expected inflation and all that. But that would not be correct, because if we use the long-term nominal rate, we face the same pitfall that we faced with the short-term nominal rate. So let me be a bit specific about this. So this is the long-term nominal rate again, up to a first order as a function of current and expected future short-term nominal rates. Okay, and now let's assume a simple root for the long-term nominal rate. Okay, now it can be shown, if you combine this with the remaining equations in the new Keynesian model, it can be shown that the condition, I mean, that's an exercise that maybe some of you have done, that the condition for a unique equilibrium is that phi pi is larger than 1. Yes, Emmy. It's working.
Oh, okay. I think this is related to the earlier comment you made about misspecification of the rule. It seems like with this long rate rule, there are multiple ways of implementing it, right? Like if you want to move the long rate up, you could either do the short rate or you could do forward guidance. How do you think about that issue?
Yeah. What is true is that a given path for the real rate, for the long real rate, is you can always back out a unique path for the short-term real rate. Okay, so it's in principle, it's if you're talking about a path. What is true, and maybe that's what you have in mind, is a particular level of the long-term real rate today. Yeah, it's consistent with.
I was just thinking about it from the perspective of like a practical central banker. So they say, okay, we're going to adopt your rule, Jordi. And then in this moment in time, you know, the real rate is supposed to be, you know, 50 basis points higher. And then I guess there are different ways of doing it.
Yeah, so I mean, one way of seeing it, is that it doesn't matter. Okay, the important thing is what the level of the real rate, the long real rate is at any point in time. It has to be at the right level. And how this is implemented, it's, you know,
so that's what I was trying to ask. Is that actually true or?
No, but through the lens of the model. If you take the model literally, and if you assume a rule for the rate, as opposed to just take a snapshot and say, okay, this is what the level should be, then you can always back out a rule for the short-term real rate, and from that you can back out a rule for the short-term nominal rate. Okay, so what I want to make clear here is that the feasible set, I mean, it doesn't expand the options that the central bank has. It just, the idea I want to convey is that evaluation and maybe the evaluation for an outsider and maybe the communication of monetary policy may be easier using this alternative rule. Okay, please.
Is your assume the expectations and losses of the term structure?
Yes. In the simple version that I have assumed here, yes, it's.
do you have an extended version where you allow for monetary policy to affect?
I don't have that, but no, I'm sure one could combine it with some theory of the term premium and get an extension of this. And I try to put it in the context of the simplest possible. Okay, so again, I don't have much time and I want to cover the empirical evidence. So let me just say that a long-term nominal rule, again, this is the interest rate. Sorry, now let's look at optimal policy with discretion. Okay, so one can show that it can be implemented with a nominal interest rate, long-term nominal rate rule that looks like this. But the observed relationship will be given by this, because this term will be zero in equilibrium. And again, you can see again that if this ratio is less than 1, then our econometrician will conclude that the equilibrium, the central bank is following a policy that doesn't guarantee a unique equilibrium, even though that's not true. Okay, so we have the same problem that we had with the short-term nominal rate. And so another question you may ask, a natural question that arises, is why a long-term real rate? Why not just a short-term real rate rule? Okay, and again, one can show here. I show assume a rule like this. The condition for a unique equilibrium is that the coefficient is positive. And one can show, I show in the paper an example, a counterexample. It just assumes optimal policy with commitment, in which an econometrician that estimates this rule, okay, will conclude that, or will estimate a coefficient that is negative. Okay, that could be, depending on parameter values, it could be negative. In fact, for reasonable parameter values, it may be negative. So again, it will lead to misled conclusions regarding the desirability of monetary policy. So let me just to conclude, show you 3 empirical illustrations of this idea, very, very simple, and at least the first 2 you may have in mind. So let's compare the long real rate versus the policy rate during the post-pandemic inflation surge. Okay, so these are, here you have, so what's the difference? Okay, the left-hand side, okay, the black line is the policy rate, okay, and the red line is CPI inflation on the left-hand side, and core PCE inflation on the right-hand side, okay, using 2 alternative measures of inflation, just to make the point that it doesn't hinge on the specific measure of the message doesn't hinge on the specific measure of inflation that one uses. So here we know here we see a well-known and well-commented fact, namely that the Federal Reserve lagged considerably in responding to the surge in inflation. No? And many commentators, thought that this was a clear evidence of the Federal Reserve falling behind the curve, and and may have been one of the reasons why inflation was so high, and so on. Okay, but now let's look at the behavior of the long real rate. Okay, so here you can see now the red line is exactly the same as in the previous picture, but the black line displays the long real rate. So you can see that from the beginning, when inflation started going up, the long real rate went up, and that's all it takes. It doesn't have to go up more than inflation. No, we're talking about the real rate, the long real rate. It has to increase, and it did increase. For the euro area, same thing, exactly the same thing. Here you have the response of you have inflation and the policy rate. Okay, again, shows a lagged, a strongly delayed response. But if you look at the long real rate, it's immediate. Okay, the long real rate starts going up immediately. Okay, so this was for the inflation, the post-COVID inflation surge. This is the past year. Okay, and here I'm using daily data based on tips to measure the long real rate, and the black line is the policy rate. So you are all familiar with this. So you can see that the pattern that the movement is far from one and from even being positive. And in particular, we see how the long real rate started going up so this must be late 2025. And when the policy rate was still going down, okay, and the shaded area represents the Iran war and clearly shows how the long real rate went up, okay, pointing to a tightening, an effective tightening of monetary policy, even though the policy rate, as we know, was flat. I don't know if I have time to mention this example. Okay, 1 minute. Very good. So this is taken. This is an example taken from or inspired by Amy and John's paper. I don't have time to provide give you the background for why they focus on this case, because it's an interesting case. So essentially, the point they make is that, look, if one looks at the policy rate in Brazil and the US during the inflation surge, one can see how monetary policy in Brazil had to be much more aggressive than in the US. And they relate this to the fact that inflation expectations in Brazil were not so anchored as in the US, and that required, a more aggressive counter-inflationary policy, whether for the US, for the Fed, it was a kind of a free lunch because inflation expectations were well anchored. Okay, I'm not going to question that explanation and its interest. I think it is very interesting, but I'm going to question the fact, namely that monetary policy was much more aggressive in the US. If you take the long real rate as an indicator of the stance of monetary policy, then you can see a very different picture. The levels are very different in Brazil and in the US for some reason that I'm not going to explore here, but they move almost 1 for 1. Okay, the pattern is very similar, suggesting that the effective monetary policy stance in Brazil was certainly not much more aggressive than in the US. Another thing is why they didn't have a better, were not more successful not as successful in taming inflation as the US was, but that's a different story. Okay, so let me just conclude again. Empirical Taylor type rules may be misleading, may suggest that policy is prima facie inadequate even when it is optimal. Okay. Through the lens of the New Keynesian model, the long real rate is the best indicator of the monetary policy stance at any point in time. Empirical long real rate rules may provide a better assessment of the adequacy of monetary policy, and simple long real rate rules may also be embedded very easily in our standard models. Thank you very much.
You have time for a few questions?
Very nice paper, thought-provoking, and answers some questions I had. So I really enjoyed it. One little quibble I have about with the regression in the middle of the real rate on inflation. It seems that if the SPF and current inflation are co-integrated, you might be picking up spurious coefficient. I'm sure you've thought about this, so let me know what you think.
I didn't think about this. I take both variables as being stationary, so I wouldn't worry about it. But obviously, I can imagine circumstances in which this may not be the case. But
Jordi, when you said that for purposes of implementation, you can back out the short-term nominal rate that the central bank should implement, is that assuming that the long-run inflation expectation is simply the one generated by the model?
yeah, it's always assumed to be 0, or constant. Okay, it can be generalized. And yes, so this is an assumption that I'm using the log linearized model around the steady state, and the assumption is that the economy always returns to that steady state in the absence of further shocks. Okay, so that's an assumption that's a standard in this analysis.
And so suppose you are doing this in real time, in the central bank, and you put the short rate on the path that will generate the
Desired
real long rate that you want. And then tomorrow morning you get a new observation of the 10-year expected inflation. Do you then change the nominal short rate accordingly,
You would have to, yeah.
having observed tomorrow morning's SPF?
You would have to. I mean, any shock that occurs would lead to a change in
Okay.
the short-term nominal rate, if that's how you implement the policy, in order to, to bring about the desired level of the long-term real rate.
Right. And if that's so, but if that's then what you're doing, what is the difference? What is the difference between that and simply targeting the SPF forecast itself? As opposed, if the object is to be focusing on getting inflation and so forth, and why not just say that you're going to keep adjusting the short rate on whatever frequency the SPF gives you an observation until you get the SPF 10-year forecast to be where you want it?
It may be equivalent. I'm not,
okay.
I haven't.
Because it seems, as if that's what you're doing, if you're responding to the SPF on whatever frequency you get it, it's not obvious to me how this is different from simply targeting the SPF.
But the SPF, this is a long-term SPF, huh?
Yes, the 10, but whatever frequency they give it to you.
Equivalence, the important, the message that I'm trying to convey here is that it has that rule that that you have in mind must be such that implements the long-term real rate that we want at any point in time. And I haven't analyzed that particular case. It could be really, it may be the case that it can be easily implemented by a kind of rule that you have in mind.
Johannes, last question.
How it similar to a short-term rate rule with smoothing. How are those two rules the same? Is there different implications for the
So how does the long-term real?
We have a long-term real rate rule. I'm wondering how is that different or similar to having a short-term real rate rule that has essentially a smoothing parameter. So like
For moving parameters, you don't even need moving parameters. No, you can have constant parameters.
Okay, so just the rho times the lag real rate.
Oh, okay. So again, what you can given this simple relationship, which again ignores term premium and so on, the one that you have, say, in the second equation that you see in the screen, you can always go from one to the other. Okay, and again, as I said, using a long-term real rule doesn't make it possible to achieve better outcomes. Not at all. I mean, you can write down a rule for the short-term nominal rate that will achieve the optimal policy with the most desirable feasible outcome. Okay, but it has the advantages that it's focusing on the long-term real rate, I have argued, allows you to see better what is the stance of monetary policy at each point in time, and it allows you to evaluate better whether monetary policy is appropriate or not. Again, but I insist, it doesn't expand your possibilities, and it doesn't allow you to achieve a better outcome. Okay, that should be clear.
Okay, we should move on to the second presentation. I think the second speaker is Ludwig. Ludwig, you're going to present, right? Yeah.
All right, fantastic. Thank you very much to Emmy and John for putting our paper on the program. We were expecting to be at a slightly more advanced stage than we are, so this is still work in progress, but your feedback is highly appreciated. Makes it even more fun and more exciting, presents something very hot off the press. So this project is called Spend What You Learn. It is joint work with Adrian, who is joining online, Matt, who is in the room, and Hugo, a fantastic grad student of ours who just graduated and is going to be at Oxford, and he's really integral to this project. Okay, so where are we coming from? The question we're going to ask in this project is, how do households form expectations about aggregate income, and does it matter how they form expectations? And really what got us motivated to think about this question is, I think, a very nice, I think highly underappreciated fact that a lot of expectations in the data seem to show patterns of delayed overreaction. So we have short-term underreaction, and then over time, as the shock persists, people become, too attached to the current present, and so they overreact in the long run. This is a term, delayed overreaction, that I first saw in work by Angelettos, Huo, and Sastry. But most of the models that capture this, in fact, all of the models that I know that capture this fact, work with a representative agent. And in a representative agent model, as I'll show you, getting the income expectations right or wrong, capturing delayed overreaction or not, really doesn't make a huge difference, because people are not going to respond to income that much. It's mostly about interest rate expectations in representative agent models. So we're going to, as usual, go towards a heterogeneous agent world and try to think, okay, do patterns like delayed overreaction about income matter there or not? So we're going to write a heterogeneous agent New Keynesian model with learning about income. So the type of learning I'm gonna mostly focus on is one where agents, I think, kind of realistically can't fully distinguish aggregate income shocks from idiosyncratic income shocks, like in sort of the Lucas Island style. So they're gonna see their income, coming in every period, and they're gonna draw from that and try to learn what that means about their future income. Now, as you can imagine, solving heterogeneous agent models isn't that simple, and then putting learning into those models doesn't make it any easier. So we come up with a new, very portable methodology, how to solve learning in arbitrary heterogeneous agent models, whether that's households, firms, banks, you name it, as long as you write these models in the sequence space. So hopefully after this, you can, implement it in all your favorite models and play around and have learning in them, which I think is quite cool. Now, conceptually, in terms of, I guess there's something here in between. I don't know if I can move this. I'm not going to try to play around with it. I'm just going to say it. So in terms of, substance, what do we get from marrying, heterogeneous agent models with learning? We're going to find that in our models, kind of uniquely different from a representative or a two-agent model, we're going to find a key multiplier that we're going to call the learning multiplier, that tells us how there's a two-way feedback mechanism between, on the one hand, income expectations, and on the other, aggregate demand. Naturally, aggregate demand affects income expectations, given that it affects realized income, and so agents are going to learn differently. But crucially, in our model, we're also going to have the flip side. We're going to have that income expectations, say pessimistic income expectations, are going to drive down aggregate demand. And then that that reduction in aggregate demand is going to give little reason for households to actually, move up from their pessimistic income expectations. So let me just illustrate why this interaction between heterogeneity and incorporating learning is so powerful. Let me just illustrate that on the next slide. Okay, imagine we sort households by their MPC. So if on the left we have the Ricardian low MPC households, and on the right we have, borrowing constrained hand-to-mouth households. Okay, and if you ask sort of how relevant are income expectations for spending, you'd see that, well, for Ricardian households, they're not that relevant because MPCs are low for those households. So even if they get a surprise in their income expectations that makes them more optimistic, they're not going to spend more. On the right end, constrained households that are hand to mouth, but by definition, they're just going to spend the income they currently receive. They're not going to spend out of optimism about the future. But it's really those intermediate MPC folks that are, somewhat forward-looking. So they respond to income expectations with their actions, and they have an intermediate MPC. So there's a meaningful link between spending and those expectations. In a representative agent model, we're just going to have the low MPC friends. In the two-agent model, we have the extremes. And in a heterogeneous agent model, we're going to get the whole distribution. And in particular, we're also going to have these intermediate MPC agents that are going to be central for the analysis in this talk. I'm not going to spend much time in the literature. Suffice it to say, there's an extremely exciting literature right now of getting deviations from full information rational expectations into heterogeneous agent models. And our paper is in exactly that literature, trying to incorporate learning. Okay, here's the roadmap. I'm going to start with just two basic motivating facts, and then I'm going to jump straight into a partial equilibrium heterogeneous agent setup where I'm going to incorporate learning. Then I'll move to a general equilibrium setup, and at the end, I'll talk about this learning multiplier that I mentioned. Okay, so what are my two facts? Fact number one is delayed overreaction. This heavily borrows on from this macroannual paper by Angeletos, Huo, and Sastry. This is off the shelf, Valerie's, original Romer shock from her work. You see the Fed funds rate going down. It's an easing shock. The unemployment rate falls. And then on the right, you see a forecast error for unemployment. This is from the SPF. And I put little arrows for under and overaction. It always trips me up. I never know which is which. So hopefully this helps you. So what you see here, you see that on impact, expectations seem to underreact. And then over time, they start overreacting because households become over-optimistic about the state of the economy. With a little bit of hand waving, I can even put spaghettis into the middle panel here. I don't know if you can see it, but that's sort of the 4-quarter ahead, term structure or forecast. You see initially these forecasts, underreact, so they're not optimistic enough, and then eventually they're too optimistic. Okay? Yes. Yes. Thank you. This is the next slide. I've tried my best. I'm not a, expectation survey expert. I've tried my best to also give you a similar plot for household expectations. This is as good as I could do it. So this uses from the Michigan survey the question about the personal financial situation in a year, computes the forecast error. Now the axes are flipped, so that's why underreaction is now positive, because it's a positive question, not a negative question. But you see conceptually, qualitatively, you see the same picture that initially you have underreaction, then overreaction, and then you kind of go more or less back to zero. Okay? And this is not super specific to just those series. In the SPF, you can look at other series too, and you generally see this kind of pattern. Second fact. So this is about how maybe we should think about how agents form beliefs. Second fact is, do those beliefs matter? And here's an interesting study from my colleague Stephanie Stancheva with two of our former students, where she surveys households and gives them different scenarios that they need to respond to. And these scenarios differ by what quarter they get an income shock in, or expecting to get an income shock. And sadly you can't see this, but the different quarters are quarter 0, you get an unanticipated income increase. Quarter 1, you expect to get one in 1 quarter, or you expect to get one in 2 quarters. And the red dots are the survey respondents' spending responses. And you see that they're quite meaningful, between 17% or so on impact and around 10% for the anticipated income increases. If I tried to match this with a representative or two-agent model, you would pretty much fail. You would get a representative model that is just flat, very low. In a two-agent model, you would get the impact response. We all know that a two-agent model can get a high spending response out of a current income increase, but it fails to respond to anticipated income increases in the future for the exact logic that I mentioned, that these agents are constrained. They're not going to respond to expectations about future income. So how are we going to be able to get closer to these dots here that are measured by Stephanie and co-authors, well, we're going to write down a heterogeneous agent model where we're going to have some households that are sort of not quite hand to mouth, but also not Ricardian. Okay, and that's what I'm going to do next. Okay, so let me start with just a standard heterogeneous agent household side in partial equilibrium under full information rational expectations. Okay, you've probably all seen versions of this. So there's a continuum of households labeled by I. They maximize a expected discounted stream of utilities subject to a standard budget constraint and a standard borrowing constraint. The key object in the budget constraint is their idiosyncratic income YIT, which is equal to EIT times aggregate YIT, where this EIT is the source of idiosyncratic income risk. That's the reason we study these models. They have nice properties, give you buffer stock saving, MPCs, and so on. Aggregate Y here is an exogenous path for aggregate income, and we're going to assume that it follows some MA infinity process around some long-run steady state. So how do we analyze the consumption behavior that comes out of this model? Well, under fire, this is a solved problem. We've worked on this ourselves, and many other people have worked on this as well. So here's the solution. If you want the consumption response in this economy to those first-order fluctuations in income, you can write down consumption also as an MA infinity, where these C hats are now the impulse responses of consumption to unanticipated exogenous income shocks. And you can say, you can stack those, that impulse response of consumption in a vector and say, compute it as the matrix vector product of a big matrix M that we've called MPC matrix or intertemporal MPC matrix times whatever the response of income is to a shock, or what the impulse response of income looks like. Okay. Let me just show you this in a picture, right? On the left here, this would be the exogenous income shock we feed in, right? That's the Y hats. How do we get to the consumption response? You simply multiply with the intertemporal MPC matrix. Easy, okay? What is this matrix? Matrix is a big generic matrix here. The columns of this matrix tell you basically how for a one-time income shock, either at quarter 0 or quarter 1 or quarter 2, consumption would respond over time. So those are the columns. The key objects that are going to be interesting to us are going to be objects above the diagonal, specifically these objects. These are objects that characterize how consumption at date 0 responds to anticipation of future income. Right, so M01 would be how much is consumption today responding because agents think they're going to get higher income in 1 quarter. Those are the objects that Stephanie and co-authors measured in their survey. And those are the objects that are going to be missed in a representative or 2-agent model, but that we're going to do a better job on with a heterogeneous agent model. Okay, so those are small in a representative agent or 2-agent. Now, this is all full information rational expectations, but the key question that we're now going to want to ask is, well, when we move away from that, what determines expectations? And so let me talk about the expectations that are underlying the FIRE model, the full information rational expectations model, and then move away to a different description. So if I just, in the FIRE model, just compute what the average income expectation is of a household, age period into the future, it looks something like this. You see that it collapses at the very right end. It collapses to a simple expression where every household says, let me count all the innovations that have happened in the past and what their contribution is to income going forward. And that's my income, rational expectations, income expectation. Now I'm going to want to move away from that. So I'm going to do the following. I'm going to postulate a specific law of motion for these expectations. And then later on, I'm going to tell you, actually, that postulated law of motion is something that comes out of very different learning models. It all comes down to a specific law of motion. So this is the law of motion I'm going to postulate. I'm going to postulate that those exact income expectations, age period into the future, are described by some matrix F times lags of realized income. So notice the difference. In the top, you think about the exact innovations that have happened and what that might imply for future income. Here, we just take realized income and say, given a certain history of realized income, these are average household income expectations. And it's not just next quarter or in 2 quarters, the income expectations, it's the whole term structure of expectations. So in terms of the little, spaghettis I showed you in the impulse responses earlier, it's like the Fs are describing what those spaghettis are in a model. Now, what is this F? I'm going to call this the forecast matrix because it exactly describes what those spaghettis look like in response to an income shock. Now, this forecast matrix is not something that, we make up and it doesn't come out of any model. And it turns out it comes of many different learning models. It comes out of a Bayesian learning model, comes out of a least squares learning model, comes out of models with dispersed or noisy information or noisy signals, comes out of models that combine dispersed information with diagnostic expectations, as in recent work by Andre Schleifer and co-authors, comes out of a model with extrapolation or structural reinforcement learning, all to first order for a first order impulse response. Okay? I'm not going to walk you through all of them, but I'm going to focus on one in particular that I think is quite nice, quite natural. Namely, that's a model with dispersed information. And the idea hopefully sounds familiar to you. It's kind of a Lucas-style idea where we're going to say, imagine that part of the idiosyncratic income that we already have in this model is not independently observable to you. So the green part there, you can observe, this was, the promotion that I got, or this was, the sick leave I had to take. But there's part that is unobservable, maybe because of overall firm-specific shocks or sectoral shocks, and you can't distinguish independently whether that was an aggregate shock or whether it was a unobservable idiosyncratic shock like a sectoral shock. Okay, and that's the model I'm gonna be working with as my baseline. But we've done the others as well, and to the extent that you can generate a delayed overreaction fact, like we will do with this, you're going to get very similar results. Now, what is this F for this special case, for this dispersed information case? Let me just show you what that looks like. And I'm going to do that under the assumption that households perceive the aggregate income to be relatively stable. And I'm doing that so I can show you what the matrix looks like. In general, if the aggregate income process is complicated, then there's a complicated learning process for households, then I'm not going to be able to, in closed form, show you what that matrix looks like. So under the assumption that households pretend all of their unobserved income fluctuations are coming from the unobserved idiosyncratic component, this is what the F matrix would look like. So it's has some entries that depend on the perceived persistence of the persistent component of that income process, and sort of a Kalman gain K-like parameter. And the plot here on the bottom left is plotting the rows of this matrix. And these rows essentially, I'm not going to have time to exactly point out exactly how it works, but essentially they tell you the position of the spaghettis relative to an income shock that happens. They tell you exactly what forecasts at different forecast horizons households are forming. Okay, I'll show you how this works in an example in a slide. So imagine we figured out which learning model we'd like to incorporate. We figure out what that forecast matrix looks like we've just done here. How do we get to consumption? After all, that's what we're interested in describing. Well, it turns out that all you have to do is you have to use the right elements of that intertemporal MPC matrix and combine it with the forecasts, with the expectations that come out of that forecast matrix. Let me give you an example. The on-impact consumption response in a model with a general forecast matrix is simply going to add up contributions to consumption out of your income forecasts at all the different horizons. These M0Hs are exactly that first row of the MPC matrix that tell you how you respond with your consumption today, if your income changes today or tomorrow or the day after tomorrow, and so on and so forth. Okay. Now, as we go to the next period, we're going to pick up a lagged contribution from this initial forecast. And then we're going to add to it a contribution of any forecast revision that happens, right? You update your forecasts in date one because in line with the changes in the forecast matrix. And then we have to incorporate those. How do we incorporate those? Exactly again with the M0Hs that we had, the first row of that MPC matrix. Okay. Now, if you do this and you keep track of all the indices and you don't make a math mistake, at the end of the day, you can write it very condensedly as the following equation. You can say in this model that no longer has full information rational expectations and instead has households learn from their observed income about potentially what aggregate income is in the future, you still have that the consumption impulse response, the C hat here, is described by a matrix vector product. With the with the exception that this matrix is no longer the fire, intertemporal MPC matrix. It's now a manipulated matrix that incorporates under the hood, which you see in this double summation equation there, all the forecast revision that will ever happen at all the different horizons. Or intuitively, how the spaghettis will form will over time as a result of the shock will influence how we need to manipulate that matrix. Sorry, Emmy, you had a question.
These are all aggregate objects in the M and the F. Am I getting that right?
Yes.
So then in the F, like, how does the aggregation work? I guess I was just thinking about this idea. You're going to aggregate first on the M and aggregate also on the F, like averaging across people, and then multiply them together.
You aggregate separately. You don't have to. That's the beauty of this.
Yeah, that's exactly what I'm asking.
Exactly. So you don't have to, recompute a different kind of M object. You can reuse whatever, full information, rational expectations M you already computed, and then use that and combine it with the forecast matrix. Now, there's one crucial assumption there to make this work, which is that the learning is the same for everyone, meaning we're not saying that if you're rich, you learn faster than if you're poor or vice versa. We're just saying everybody's subject to the same learning friction. They might get different signals, but those signals are orthogonal to their other states. Johannes.
Yeah, I was wondering, are there any restrictions on how the income charts to get that separation between the M and the S? Right.
Yeah, perfect. The key is, I'll go into more detail in a second. The key is that the observed and the unobserved components need to be orthogonal. That's the key. If you say, we can play around with correlations, then you're not going to have that coming out right out of the box. But I think it's a useful starting point just to get some traction, and then we can play around and say, there's different signal positions. Maybe some people maybe know more than others, but that's our baseline right now. Thank you. Okay. Now let me show you an example. Okay. And this is all partial equilibrium. I'm just going to pick a path for the income shock, hit them with it, show you what happens. Okay, so here on the left, I'm doing the simplest possible income shock, a one-time negative income shock that then goes back to the steady state. So that's an aggregate income shock. What happens to household beliefs here? Well, households partly mistake that for an idiosyncratic shock. So they're like, okay, not sure if this was an aggregate shock, maybe it was just my industry. And so they're going to think that there's a chance that if it is an idiosyncratic shock, there's a chance that it was IID or that was the AR1 component of their idiosyncratic shock. And so that's why you see that there's a little bit of persistence in the beliefs. I hope you can see that in the spaghettis there, but not a lot. So there's a little bit of overreaction you get from that because there's some pessimism that people get from getting that negative income shock, but not a whole lot. And so that's why the fire and the dispersed information lines are relatively similar. Now, if I take that same idea and make the shock more persistent, this is an AR2 shock. You see that what happens to beliefs is that initially households under-respond, but then the longer the shock persists, the more sure they become that actually this is a persistent shock. This is not going to go away. This is, this is the car industry, faltering. So I'm not going to have, the same income growth that I expected typically. And so they become very pessimistic. And so you see that in a dispersed information model, especially in a heterogeneous agent model on the right, you get after this initial underreaction, because households are slow to learn, they become very pessimistic and they reduce their spending by significantly more than they would have in a full information rational expectations work. Okay. So this is delayed overreaction sort of in partial equilibrium already. But this is all partial equilibrium. So what I'm going to do next is I'm going to, let me just skip this. I'm going to go into a general equilibrium version of this model where we can then make whatever we fed in here as exogenous income shock endogenous to household behavior. So I'm not going to give you many slides of model introduction. The model is, staying very close to the existing literature. So we're going to have a household side here that has exactly with income exactly of the kind that I mentioned. There's an observed and an unobserved idiosyncratic component. These are orthogonal, and households can't distinguish the unobserved idiosyncratic component from the aggregate component. We assume that both of these components have the same income process, an AR1 plus an IID. That's going to be crucial. That's going to be the nature of first under, then overreaction. That's going to be what disciplines that. We're going to have a linear production function with sticky wages and flexible prices. We're going to have set a real interest rate rule, and we can now all side majority for that, and everybody's going to be fine with it, hopefully. We're going to have a government that sets a proportional income tax rate and adjusts it to balance the budget, and everything is going to be quarterly. And last but not least, let me emphasize that in this model now, because it's GE and because income or GDP is endogenous to what happens in the economy, we're going to have to solve a fixed point. This is the sort of the infinite regress style fixed point, because whatever determines the actual realized path of aggregate output will affect how agents learn about aggregate output or income from their own observed income. So there's a little bit of a fixed point there that we have to solve, but it's not a problem at all with our technique, even in a heterogeneous agent setup. Okay. Now, why do we like our heterogeneous agent model relative to a representative or two-agent model? Here's the exact plot from before. I just put in a line for our heterogeneous agent model. We target the same on impact MPC all the way on the left side here. And you see that it does much better in generating reasonable responses of spending to future income surprises, whether they happen in quarter one or 2 quarters in the future. Okay, and that's entirely what's going to drive the difference between our model and a representative agent or a two-agent model. Now, just to make sure that our model actually does generate delayed overreaction, we fed in a monetary policy shock. We did so in the simplest possible way. We just tell everybody this is the path of real interest rates. But we're not telling everybody, oh, now you know what the income path looks like as a result. We're telling them they still have to learn from realized income about future income. So it's not a FIRE model. It's only FIRE with respect to real interest rates. And you see that, GDP becomes hump-shaped as a response. And you exactly see in the right panel there, initially, households under-respond, their expectations underreact, and then their expectations overreact, exactly like they did in the data. Why do they underreact? Because the first minute their income goes up, they're brushing it off. They're like, it's probably just the IID component of my income. It's probably just a fluke that I got lucky this year, got a little bit more income. As it persists, they're starting to think, oh, maybe this is, whatever, a sectoral shift that will stick with me for longer. And only then are they going to start learning, okay, look, turns out everybody is in the same boat here, so maybe it's an aggregate shock, okay? And that process will give you exactly that under, then overreaction, and then going back to zero forecast errors. So in my last few minutes, let me talk about, I think, a very interesting prediction that comes out of this model that we're going to call the learning multiplier, okay? So let me illustrate this with the following experiment. I take the GE model and I take the income reduction that I just fed in, exogenously, this AR2. And I ask, let me generate that as a result of a GE model that is hit by a demand shock, which I simulate as a beta shock, okay? And I do so in a FIRE model. So I start with a FIRE economy, feed in a beta shock so that the GDP output response exactly has this AR2 shape. And then I ask, What if we now fix the beta shock that gives you this recession? And I go from FIRE to the dispersed information model that I wrote down that gives you this delayed overreaction. What happens to GDP in that world for the same fundamental beta shock? And it turns out you get a much larger recession, and what I want to emphasize, a much slower recovery here. Why is that? It's precisely because initially households under-respond, but then they become so pessimistic about the future that they start spending less. And if they start spending less, the economy isn't recovering. And if the economy isn't recovering, why should they update their pessimism? Why should they get back to normal expectations? That's the overreaction bit in the forecast error. Okay? And so it's harder to kind of move outside of a recession here in this world. Now let me compare that with a representative agent economy. I'm going to do the exact same experiment. I'm going to say, give me the FIRE model for a representative agent. Make the FIRE model match that same recession. And then remove FIRE and replace it with the exact dispersed information setup that I've put into the heterogeneous agent economy. And this is what you see there. So the yellow lines or orange lines are the representative agent model with dispersed information. Now, if you look on the right side, that model does give you under then overreaction. It does give you delayed overreaction. But the effect on GDP is much more muted. Why? Because Ricardian agents in that model are not going to spend much in response to changes in expected income, because their NPCs are small for any sort of realistic horizon over which their income expectations change. I can do the same thing for a two-agent model. And it turns out for the two-agent model, it's on top of the representative agent model. I'm not going to go into exactly the details for those in the room that are interested. It's exactly because the moment I turn a Ricardian agent into a hand-to-mouth agent, I lose an agent that would have at least responded somewhat to changes in income expectations. And I gain an agent that amplifies everything within period. Those turn out to exactly offset one another. So I think this is a good case for exactly those intermediate NPC agents that a heterogeneous agent model generates. Now let me do an experiment with this. Imagine we're in the slow recovery, say Q8 or so, and we've not done anything with interest rates. This is constant real rates, but now we wake up and we're like, oh, let's stabilize the economy. How hard is it going to be to get a heterogeneous agent model with sort of entrenched pessimism out back to steady state output? It's a question about the natural rate. And this is what you see here on the right. So on the right, the dashed line shows you that if in Q8, I wake up and I'm like, all right, enough with this recession, let's stimulate to get output back to the steady state. You see here in the dispersed information economy, you have to cut rates a lot. Why? Because it takes a big push to get people out of the rut that they're in with pessimistic expectations to get the economy back to steady state output. If you compare this with the dashed line on the left, the FIRE economy, there's no big problem at all. You don't have to lower rates by more simply because you missed the recession for 8 quarters. Now, had you started stabilizing from the get-go in both economies, and that's the solid line here, it would have been roughly the same. So in some sense, there's a bit of a higher cost here if you sit on your hands and you don't, you let the recession take its course, because if you want to course correct later on, it's going to be more costly because you have to stabilize more. You can also do something interesting where imagine we are in this world where we stabilize in Q8, but say we want to get interest rates back towards zero faster. So we want to, overheat the economy so that we're able to get the natural rate back to zero faster. We get interest rates back to zero faster. It turns out that that's something you can do in this world. So if you look on the right plot here, if you let interest rates sit around sort of the lowest point here for a little longer, then you can raise rates afterwards faster, because the natural rate, while you keep easing, the natural rate moves up. Okay. And so this gives you a temporary overheating on the left in output, but it helps you kind of push up your natural rate faster. Why do I think that's interesting? Because many models that we typically write, models with capital, models with durables, like in Alistair's work with Johannes, models with debt, typically have the opposite. Typically have that when you ease, you bring down the natural rate as you keep easing. Here it's kind of the opposite. You increase the natural rate as you ease more, which I think is kind of interesting. Okay. Last but not least, let me do a very bold experiment just to put numbers on the table. Okay. And what I'm going to do is I'm going to take the Great Recession, as you see here in the left, real GDP detrended. And I'm going to just assume, for the sake of just today, that this was just caused by beta shocks in the model. And I'm going to assume that it was caused by beta shocks in the model. I think is the right one, the one with dispersed information. Okay. So you see here, the black line is GDP, and on top of it, my green dashed line, that's the dispersed information fit. And by construction, it fits. You see the gray lines, if you squint, those are the forecasts of the agents in my dispersed information model. You see, initially, they're kind of too sanguine about the shock. They think, oh, it's going to go away, it's going to be temporary. But then as you look in the trough, as you linger in the trough, they become more and more pessimistic in the model. And at some point, they're overly pessimistic. So the forecast error moves into overreaction territory. Okay? And now I'm going to do the flip side of what I was just doing. I'm going to say, well, save that beta path that gives you that recession. And now undo dispersed information. Assume we had full information ration expectations here. How would the recession have looked in that case? And this is the dotted blue line. And you see that in that case, the recession would have been much less persistent. So the blue line, you see, it just goes back much more quickly here. Obviously, don't take the numbers, literally, but I think it's a sign that there's some entrenched pessimism that can actually meaningfully delay the recovery from a recession. And the faster we can fix a recession, the better, because then we don't have this entrenched, pessimism problem. I'm almost done, Amy, and then happy to hear all of your questions. I can do the exact same experiment in a representative agent model. This is on the right here, and you see there's almost no, faster recovery in fire relative to the dispersed information model, which I think is interesting. Let me conclude. I hope you learned something today. So this is a new approach to embed learning in the sequence space. We have this application to learning about income in a heterogeneous agent economy. I think there's a really powerful interaction between learning as a deviation from full information rational expectations and these intermediate NPC households. I think they just naturally want one another. And there's this, I think, very interesting idea of a sort of learning multiplier that comes out of these models that can maybe explain why some recoveries from recessions take so awfully long. Thank you.
Okay, a great presentation. The question I was going to ask is I was trying to understand how you were thinking about trends because you did the detrending, but I would have thought that a big part of what people are learning about, for example, in our paper, that was a lot of what was going on is how much is the trend and how much is the cycle. And of course, one of the features of the standard macro model is that things are very trend stationary, but of course the data looks more different stationary. And that's, so when people are extrapolating things into the future, one could say that that's, irrational relative to the model. But of course, if you look at the data, there is actually a lot of persistence. So I was wondering how you thought about the trends in the data versus in the model.
Great. Right now, there's not much about trends here, but that's something that's on our to-do list of putting in a trend component that you can learn about, which right now it's not here, it's all stationary. And I think that'd be very interesting to incorporate in the model as well. Thank you.
Estimates potentially recession went on. So that's another way to forecast.
Yes. Perfect. Thank you.
Rafet?
Interesting study the implication for pricing.
Yep.
If you take these households and match them with firms that don't suffer from the same problem. I guess inflation will lead output strongly because I see GDP going down a little, but I know that it's going to go down a lot because the idiots are going to overreact in the future, right? And in any call setting, that's going to make me look a lot more today. But so that I can see, but I have no sense of what would happen if the firms are behaving this way, whether these two things will interact, whether the price setters are also trying to figure things out.
Yes, I think that's very interesting. I mean, part of why I like, and might be my biased self, I like this approach is because I can easily put it into a pricing model. I can even, not even just Calvo, I can do it in menu cost, whatever you like, because it's one tweak. It's just this additional matrix I can put in. So I can have I can have a model where I have not fire price setters, but, dispersed information or any other Bayesian learning price setters and then look at the interaction with households. I don't know exactly what would come out of that. I think that'd be very interesting. On the same line, I think, thinking more about financial markets, right? That's the complement to what you said as well. And we know there's lots of, biases in their beliefs as well that I think be really interesting to incorporate in these kinds of macro models. 100% agree. Yannis.
This is equivalent to what definitely did for C2 algebra, like it would be like the big use GitHub shop that I think would discipline the learning piece of the model, like the under and overreaction, get to GitHub shop that don't actually materialize when you learn that. And I think both these pieces together, that would together.
Right. So I like that at least we have sort of that first row. I agree, it'd be nice to then say, okay, what happens then when your forecast from yesterday actually doesn't materialize? Now, for some of them, it's okay. I think I have enough information to discipline that, because imagine what happens is, you tell your study participants you're going to get $100 next quarter. You ask their response. That's what Stephanie does. And then you fast forward to next quarter. Imagine they're not getting their $100. That is like an unanticipated negative income shock to which you should respond like you respond to an unanticipated negative income shock today by linearity, right? So I think for some of these sort of experiments, if they're not materializing, it's almost like just the difference between, two columns, quote unquote, of that matrix. But for some of the later out ones, we don't have enough information to really get at exactly that experiment. But I'm happy that we at least have, some evidence on that first row, but I welcome any additional information that we can get.
Okay, we should probably break now, and let's reconvene at 3 p.m.
So.
Thank you. Down, nice down, something like that. Cancel out. Now. I'm just working on that. You know about. Learning is now it's just never received spaghetti plots. As you had in your paper. So, I mean, we're working on some, we're using your thing. Great, we're finding it here. I need more guys. Yes, you're
Okay, let's get this back on the road. So, the next paper is about when the Fed reveals its hand, and Andrew is going to present. Take it away.
All right, so thank you to John and Emmy for including this paper on the program. This is joint work with Tara Sinclair, who's in the back there. So the motivation for this talk really comes from the fact that central banks, including the Fed, regularly release their economic forecasts, their macroeconomic forecasts. So this table right here is just pulled from the most recent summary of economic projections, or the SEP, where they release forecasts of GDP, the unemployment rate, inflation, core PC inflation, and then also the Fed funds rate. And so the question that we're trying to ask is, given that the Fed and central banks are releasing this in conjunction with their monetary policy decisions, how does this change how we think about understanding monetary policy, or how might markets be reacting to this? And one kind of tidbit or idea of thinking about this comes from a quote from a capital management firm after the December 2022 meeting, where they highlighted this discrepancy between the Fed's view of where the economy was going in terms of inflation being higher and persistent for longer, versus the market's view had been expecting inflation to be coming down. And so how do we kind of incorporate this kind of thinking, this kind of information in terms of our thinking about understanding the effects of monetary policy? Okay, so what we're going to do is we're going to really start by thinking about really starting from this literature on the identification of monetary policy shocks, and in particular this literature on the high frequency identification, looking at these very narrow windows right around the FOMC statements. And this literature, it's already pretty well known that these aren't just capturing pure shocks, they're also capturing things like the response to news or potential central bank information effects. And really what we're going to be arguing in this paper is that these forecasts release are really a clear, important channel for the release of central bank information. Okay, so what we're going to do then is really start by formulating a theoretical framework, okay? And a theoretical framework which really builds on the existing literature, but is really allowing for the intermittent release of these forecasts. So you're going to have a release of forecasts every other meeting. And what's going to happen there is with the forecast release, you're going to have two things going on. You're going to have a release of information that the markets can react to, but then in the non-release periods, you're going to have markets basically anchoring on that information as a clear signal about kind of the Fed's view of the state of the economy. And so what this is going to allow us to do is to make kind of two predictions that we can then test empirically. So the first is that we're going to predict that surprises are going to be systematically larger when you have these forecast releases, okay? And we're going to do this, we're going to kind of test this empirically by looking across 19 alternative high-frequency measures, and we're going to show that on average, these monetary policy surprises during these release meetings are about 2 to 3 times larger than non-release meetings, okay? So that's the first. So we're going to see larger surprises with the forecast release. And so the question is, what's driving that? Now, our theoretical framework says a lot of what's driving that is going to be the information surprise itself, okay? So the idea is that if you control that information surprise, you should be getting roughly the same about a size surprise that you would otherwise, okay? So to kind of test this, we're going to use a unique Bloomberg survey that asks financial market participants basically what their expectations about the SEP was right before the FOMC meeting, and we can use that to essentially construct these information surprises and show that that explains a lot of, or the vast majority of this additional variation from these SEP release meetings. And finally, we're going to do an empirical exercise where we're going to sort of re-examine these Fed information effect regressions, particularly looking at how professional forecasters are revising their expectations on core PCE inflation over the next year. And we're going to see that they're going to be responding to these SEP surprises, in particular these inflation surprises, okay? So this work really touches on quite a few strands of literature. I'm not going to talk too much about them, but we're really touching on this kind of contamination of high frequency monetary policy surprises, the broader literature on central bank information effects, the kind of thinking about summary of economic projections, then the FOMC forecasts in general, kind of this idea of how we disentangle monetary policy surprise and monetary policy shocks. And we're also tying into thinking about central bank communication, okay? So for the rest of the talk, I'm going to go into the theoretical framework and go through that, and then touch on the predictions and testing the two predictions that we get from the theoretical framework, and then finally re-examining this information effect regressions before I conclude. So in terms of the theoretical framework, we're really starting by building on kind of what we call the existing literature. And this, what we're building on is really, so the Bowen, Swanson, and Jarodzinski and Karate 2025 literature. So you can think of there being a kind of a state of the economy. You can kind of broadly refer this as an output gap, that it's evolving dynamically over time. And the central bank and private sector are kind of the two actors in the economy. And both of them are going to have essentially a private signal of what the state of the economy is.
Another interpretation of the higher variance of shocks is that for the longest time, the SEP meetings were the only ones with press conferences, and it became assumed that nothing would ever happen.
We'll talk about that. We'll talk about that. So great question. So we have these two private signals that we're having. So the central bank is then going to set interest rates based on its reaction function that it knows and its private signal, okay? The private sector then is observing its own private signal, but before observing the interest rate, is going to set expectations about the interest rates based on its own private signal and its kind of estimate of what the reaction function is. So then the monetary policy surprise that you get out of that when interest rates are set is going to be really two components. This response to news effect component, which is really that kind of reaction function error term, and a central bank information term, which is really the difference in their private signals, okay? Plus that shock term, the epsilon, which people are typically what they're most interested in. Okay, so this is kind of where the literature was when we started, give or take some assumptions to either shut down one channel or the other. So our question was, how do we incorporate the release of the forecast into this sort of framework? So what we're going to do is we're going to extend this to think about what we think of as lumpy forecast releases and perfect proxies. So we can think of every other meeting, the central bank is releasing a signal essentially to the public along with its interest rate decision. And that signal is really going to be a noisy measure of its own private information. Okay, and you can think of the SEP median being a measure of this. Okay, and so you think about the median is a median of all FOMC members, not necessarily voting members, not necessarily all members are submitting forecasts. So it's really a proxy of an information set. Okay, and this is being released to the public. Okay, and they're only doing this every other meeting, on and off. Okay, and so how do we think about how this is going to impact these monetary policy surprises? To interpret this, what we're going to do is we're going to make very strong assumptions and to help you kind of see what this looks like, and then we're going to relax those. So the strong assumptions that we're going to make initially are that the private sector, once that forecast is released, once that signal is released, they're going to completely anchor to that signal. They're going to say, this is what the Fed views as the state of the economy, and until we get something new, that's what we're going to hold on to. Okay, so they're going to anchor on to that. We're also going to assume that the central bank is only updating its forecasts when it's releasing them. Okay, so when it's not releasing its forecasts, it's going to relieve them constant. And there's some empirical evidence for some weak aspects of these assumptions, and particularly this quote from Chair Powell. Former FOMC Chair Powell indicates that there was some holding on to their forecasts even over periods of time. Okay, so we're going to start by considering each meeting type separately. So looking first at the forecast release type, where they're releasing the meeting. So here, not much is different. The private sector knows the central bank is going to update its forecasts. It's going to make its own updated expectations based on its own information where it thinks the central bank is going. And so it sets its expectations. The central bank updates its interest rate based on its own rule and its own data. And so the surprise is basically identical to what you would see before. The only difference here is that really the market can see that information differential, or essentially a proxy thereof. So they can learn quite a bit from this differential because they know what that forecast proxy is, and so they can learn from that. Okay, so that's the release period. What happens in the non-release period? So in the non-release period, we're making these strong assumptions. We're saying the private sector had observed the previous forecast, and they're going to anchor to it. And they're saying the Fed is still sticking to this same trajectory, okay? Just one step further along this trajectory. So they're going to estimate this reaction function based on that anchored forecast. The central bank here, again, is not updating its forecast, so it too is just moving one step along its known trajectory. So the surprise you're going to get here is something that looks a lot like just a response to news effect, plus some additional noise. So that additional noise is essentially capturing how good of a proxy it is that you're releasing, okay? And so what you have here is in the release period, you've got this full-on information effect. In the non-release period, you've got basically no information effect at all. And assuming you have a very good proxy, then you've got something that looks a lot like a Bauer and Swanson, just purely response to news effect. Okay, so that's going to create a wedge between these two meeting types. Okay, so this is really strong assumptions. What we can do is we can relax these and say, well, let's allow for some amount of anchoring determined here by gamma. Okay, so they're going to sort of react smoothly between complete unanchored and complete anchored. And you can think at the same time, the central bank's going to update either, could update a lot or could update not a lot. And so in general, you're going to get something, more general. So, I mean, ultimately, those results are going to depend on your choice of gamma and your, in terms of the anchoring and whatnot. So you can go through and look basically across that kind of response surface. But, in the interest of time, the key result here is that this wedge, this information wedge between the forecast release and non-release meetings is going to exist as long as there's some degree of private sector anchoring, okay? And additionally, the clearer your signal it is that you're sending from the central bank, that's going to increase the wedge as well, because essentially otherwise you're adding noise to the non-release meeting. This, the additional point is that the central bank forecasting updating doesn't matter as much as particularly as long as there's a persistent process. So if you think inflation is high and the central bank is saying inflation is high, you're moving next period and inflation stays high, that doesn't matter so much. It matters a lot more if you're kind of moving in and out of recessions and expansions, then that updating matters a lot more. Okay, so this is kind of the broad idea of this framework that we're setting out. And so really what it does is it allows us to think about what are the predictions we can think about from this model. And the first prediction really is that monetary policy surprises during meetings with these forecast releases are going to be systematically larger than those without forecast releases. Okay, so on average, you would expect that higher volatility. The second prediction is going to be if forecast releases are a reasonably good proxy of the true information set, then conditional on that information, that difference should go away. Okay, so that difference should go away. And that should also somewhat deal with John's question about, is there something else driving this other than information? If there's something else driving this other than information, then that prediction should not hold. Okay? So what we're going to do now is we're going to go through and test these predictions, for the rest of the paper. So for the first prediction really is monetary policy surprises are larger following these SEP release meetings. Okay, so to give you a little background on the SEP has been released by the FOMC since late 2007. Okay, in 2007 they were releasing it with the FOMC minutes. Okay, well after the FOMC decision. So in 2011, what they changed this, where they introduced the press conference and they released the SEP shortly after the statement, but before the press conference. Then starting in 2013, they're releasing the SEP simultaneously at the exact same time as the FOMC statements. So we're going to be really looking at this post-2013 period. Okay, so what we're going to first look at is this measure by Bauer and Swanson. So Bauer and Swanson looking at this high frequency measure, and they're partialing out, trying to remove all the news effects. Okay, so there shouldn't be anything else that remains. So we're going to look at that across several different time periods. The first time period is really a pre-SEP era. The second time period is this SEP era, and then you have the different blocks within that. So the kind of dark orange bars, that's all meetings. So that's the mean absolute value for all meetings. Then we remove the recession era and kind of unscheduled meetings. There might be other things going on. There's never an SEP for those meetings, so we're going to remove those. So you got those are the tan bars. And then we're going to kind of disentangle those tan bars and look at the non-SEP versus the SEP. Okay, so for the pre-SEP era, we just put in hypothetical dates that will match with when the SEP occurred. And you can see there's no real systematic difference between those. So there's no like seasonal effects that you might say, well, it's always the September or December meeting that are large, just naturally. Okay, so what you get then first on the left-hand side is the 2008 to 2012 meeting. There was an SEP being released, but it was not simultaneously with the meeting, so there's no difference. So then starting in 2013 to 2018, you get this difference, okay? Now, you might be saying, well, that might be really related to press conferences. Well, since 2019, they've been releasing the press conference. They've been doing a press conference with every meeting, and you're seeing since 2019, there's large discrepancies there, okay? So this is just one measure, okay? And there's no statistical significance or anything here. So what we do then is we run a regression. So we run a regression of looking at the absolute value of that surprise, estimated on a constant and a dummy variable, whether there's an SEP or not. Okay, we're just testing whether that dummy variable is statistically significant. And then we're going to plot this in a normalized way, where we're going to plot this all relative to normalized to 1, where it's no SEP. And so if it's larger than 1, the SEP is some fraction larger. Okay, and we're going to do this across 19 measures. Okay, Here's what that is ordered from largest discrepancy to smallest discrepancy. So on average, you're seeing in the range is really from 1.5 times to 3.5 times larger. So there's quite a bit bigger. Across all of these, it's larger. 18 of the 19 are statistically significant. You could do some corrections and it would fall further, but the vast majority of these are significantly different for SEP meetings, okay? Now, the Bowen-Swanson measure that we're looking at is really just in the middle. It's kind of it's around 2.5 right there. So it's not the largest, right? And you can think of some, for the largest, there's stories you could tell, but the argument here really is that these SEP release meetings, the surprises from them are quite a bit different than the non-SEP release meetings, quite a bit larger. Okay, so then the question is, what's driving this? Okay, and our argument with our theory is that this is information surprises. So controlling for these information surprises should capture most of the differences across these meetings. So how do we construct these information surprises? So what we're going to do is we're going to look at this pretty unique Bloomberg survey that has been conducted since December 2017. And it's been done basically the week right before each SEP meeting, in which they ask these market participants basically, what is your expectation of what the SEP forecast, the median SEP forecast is going to be? And they ask that for all the variables and all the horizons. So then what you can do is you can construct these SEP surprises or information surprises based on the actual SEP release and then what the market kind of expected that SEP to be. Okay, and so then we can look at that, and this is just provides a picture of the variation of those surprises over time. So you have that for each variable: federal funds rate target, GDP growth, unemployment rate, PC inflation, core PCA. The main thing is that there's kind of variation in these surprises across all variables and all horizons. And so then the question is, well, does this information explain the monetary policy surprises, okay? So what we're going to do is we're going to go back to this Bowen-Swanson measure, which again has orthogonalized out the response to news. So all that should be remaining, if there's anything at all, should be central bank information. This is actually biasing our results against us, because if to the extent that there's any central bank information that's correlated with the response to news, then it should be pulling that out as well. So we're going to look at that measure and say how well these surprises can explain that. And we're going to look at two different ways of kind of reducing this dimensionality using kind of either a real-time Taylor rule constructed off of the median SEPs or a kind of principal component analysis, really data-driven of the SEP surprises themselves, okay? So that's what we're going to use, and these are kind of the results. So looking initially at that inertial Taylor rule, we can find, this is the inertial modified real-time Taylor rule. We're just replacing the median forecast with SEP surprises and seeing how well it explains the Bowen-Swanson surprise, monetary policy surprise. And you're getting roughly 65% of the variation in that surprise. Now, the concern here, of course, is the inertial Taylor rule, and you're essentially using a federal funds rate target surprise to explain the monetary policy surprise. So you'd think there'd be some endogeneity. So when you kind of go to a static rule or an IV of that rule, then that explanatory power falls, but you're still getting about 30% of the variation. And really, it's really the principal components gets you something similar. So explaining around a third of the variation in that the monetary policy surprises during these SEP meetings. The key thing here, of course, also to point out is it's really loading a lot on the 1 year ahead horizon and not so much on the shorter horizon, where you'd think a news effect would be loading much more on a shorter horizon. Okay, so what does this mean in terms of explaining the differential between an SEP release versus a non-release? So this is just the same result that we depicted before, where about an SEP release for the Bowen-Swanson measure is about 2.5 times larger than a non-SEP release. When we partial out or remove the principal components of the information surprises, then that drops dramatically to around like 1.5, and it really is no longer statistically different from a non-SEP surprise. So this really looks a lot like those information surprises are explaining most of that differential. Okay, so what are these information surprises? How do we think about those? So what we do is we decompose this Bowen-Swanson shock into the SEP information and then everything else, which we can think of as something much closer to exogenous, right? And so the gold bars are the SEP information and the blue bars is kind of everything else. And so you can see that really a lot of what's going on here is really in that post-pandemic inflation period where, you're seeing these positive surprises and it looks like, a lot of that is driven by inflation, information.
Really think of these as information about non-monetary stuff. But SEP also has the FOMC's self-forecast. So, do you know which components it likes?
So the principal components here, we're only using the macro forecasts. Okay, so we're only using the macro forecast surprises. Okay, so we're not using the federal funds rate surprises. I don't know if that helps.
So it would be correlated.
Yeah, yeah, one hope, right? Yeah. So yeah, they are, but this is really going to capture, that surprise is going to be relative to what the market is looking at, right? And so, here, let's look at the next slide. And so what we do is we decompose these information surprises, and we decompose them into the different variables that we have in the principal components, okay? And so this kind of gives you a sense of, it could be, this could be also learning about, this is information that they're using to learn. It could be learning about a reaction function, which ultimately is ultimately going to all kind of related together. But this is really in that information type surprise. And so really a lot of what's going on here is driving these swings in the surprises in inflation. In particular, that the quote I highlighted in December 22 is really kind of showing these positive information surprises. And some of the only negative information surprises are in the periods right after tariff announcements. So when the FOMC was less expected that the tariffs to have less of an effect on inflation than the markets did. Okay, so here's another thing that I think will help isolate these information effects, where what we're going to do is we're going to revisit these kind of Fed information factor regressions. Okay, so we're looking at how are private sector forecasters updating their inflation expectations following this monetary policy shock. Okay, yes.
This story seems to imply that the SEP is a better forecast of inflation or growth than the SPF on its own.
I don't see it that way. So I see it as, regardless of whether it's good or not, the market views it as important information, especially if it's giving information about the Fed's own thinking. So I think it's important information, or being treated as important information by the market, regardless of how accurate it might be ultimately.
So this is a story that applies to 2013 on. A lot of these Fed information corrections are about the 1990
Right.
to 2007, 2000.
Right. Right.
For which there's mostly not an SEP at all.
Correct.
So you don't have anything to say about those earlier.
No, not in this paper. This paper is really talking about kind of the recent SEP innovation in terms of how that could be a clear information effect signal, and not anything about prior. That's correct. Okay.
You would make a prediction that there should be an information effect post 2013, but not before. But I think that's not consistent with the data.
So, we would argue that so we're not saying per se that the SEP is the only information effect. We're saying it's a very important information effect, okay? And so we're not making a statement about this pre-period at all. We're just really looking at this sort of, how do we think about interpreting the SEP release and how that might be functioning. So let me just get on and hopefully answer some additional questions where we're going to look at these information effect regressions, and we're going to look at how private forecasters are updating their forecast of core PCE. Okay, and so what we do, we first look at just this raw monetary policy surprise. And so initially you're getting this, what looks like this price puzzle, right? So you have a positive monetary policy surprise, upward revision in inflation expectations. If you partial out the news effects, that goes away, okay? No longer significant, okay? But then what happens if we then partial out the SEP surprise information, well, that is starting to turn negative, the coefficient's negative, and you have kind of a weak positive coefficient on the SEP surprise. And then if we decompose that further, you can see that forecasters are reacting negatively to potentially the monetary policy shock, but very positively to the inflation information surprise. Okay, so that kind of suggests, at least to us, that this is a lot more than just an interest rate response or whatnot. Okay, and we can control for the Fed funds target rate surprise, and this result stays the same. Okay, so we've gone and done this for individual forecasters as well, and you get similar results. In fact, you find that individual forecasters are responding both to their individual surprise relative to the SEP, as well as the common kind of consensus surprise. And we find this result for both forecasts of unemployment and core PCE inflation, not necessarily for GDP. We also find that this is robust to kind of thinking about controlling for any news releases or sort of even pure and time fixed effects. We've looked at inflation expectations, looking at high frequency movements and inflation expectations around the window, and find that most of the movement is really at the long end of the term structure, so 4 years plus. And then we've also done these kind of local projections, vector autoregressions, to see what the effect is, and we find that it's very much consistent with these kind of information effects. So really, just to conclude, we find that these release of forecasts by central banks are a key channel for information transmission. Following these SEP releases, the surprises are systematically larger than when there are no releases. Our theory suggests that this is really information plus anchoring, and controlling for this information seems to really capture most of this differential. And you're seeing clear effects on both inflation expectations and the macroeconomy. And ultimately, I think the key kind of takeaway is that communication choices by the central bank have implications for the macroeconomy, and they also have implications for how we kind of study and understand the effects of monetary policy. So thank you very much.
So we have a good amount of time for questions. Rich?
So I enjoyed this paper. Two comments. First, there's a complementary data set to the Bloomberg SEP survey. There's a survey of primary dealer market participants the New York Fed does, which is very granular, almost navel gazing. But it actually, so it overlaps with Bloomberg, but it actually asks some other questions. So you might want to look at that. The other thing, which is that the SEP actually provides information on the individual participants' assessments of balance of risk, which the press oftentimes does not focus on. But if you sort of do an eyeball regression, I think it is informative. So you will see periods where the SEP medians are not moving. But when you ask participants, is the balance of risk to your inflation forecast to the upside or the downside, they'll be saying upside or downside. And I've not seen a rigorous study of that information, but I would be really surprised if it has zero value as an indicator. But again, really enjoyed the paper. Thank you.
So those are great comments. So first, on the survey of primary dealers, we have looked at those. And in particular, it's quite interesting because on the survey of primary dealers, they ask forecasters what their forecast of the economy is, simultaneously with what their expectations of what the Fed's view of the economy is. So you can use this. So that's something we're still kind of looking at, is because you can have this discrepancy not only between what markets think the Fed thinks, but also what markets think the Fed thinks and what they actually think. So there's a lot there. So yes, that's really interesting. On the balance of risks and uncertainty, so they've only been releasing the risks and uncertainty publicly since 2020. They have a series that is effectively real time that goes back to since they've been releasing it.
Maybe if I can just educate. So the available time series only began to be introduced in 2021. But it used publicly available information that was in the older
Right.
surveys. And so, you know, if you use it, you might want to footnote that
Right.
this data is not new. It was always revealed, but no one or no vice chair went to the trouble to say, let's do a chart of this, so you don't have to go dig up the past 38 issues.
Yeah, so I will, yeah, we are looking at the balance of risks, and that's also ongoing work. We've controlled for the uncertainty measure that they also produce, and that
Yeah.
doesn't seem to be somewhat, but the balance of risks, yeah, so that's a great point.
So I kind of wanted to re-ask what I understood to be Rafit's question. So the SCP contains obviously a lot of information about the Fed's beliefs about the economy, but also a much clearer picture of the Fed's beliefs about its own reaction function.
Right.
So I appreciate that you're only using the non-interest rate variables in your regressions, but as Rafit pointed out, they could be correlated with the interest rate variable. So how are you distinguishing between those
So
two?
I mean, I think this is the clearest picture. So this is the individual regression. So so I'm looking at all individual forecasters in the Bloomberg and how they're revising their expectations. And so if the rightmost column, you look at this is just the kind of surprise, the raw surprise effect. And then what we're doing is we're controlling for the Fed's fund target rate surprise. Okay, here we're completely controlling for any information they had about the dot plot, and you're still seeing that they're responding to PC and core PC inflation. So that suggests to me that yes, the target or the dot plot really matters, but it's not just the dot plot. So thank you.
And I guess you could create some kind of partial R squared, which is only once you've done this, taken out this coefficient or something?
Right. Yeah. I mean, so yeah. I mean, this is here we complete time fixed effects and everything. So here you're getting roughly about 10%, and here the Fed funds target rate surprise completely goes to zeros, is in irrelevant, but it's really still the core PC and PC inflation surprise that matter for this. So and yes, we could do a partial R squared as well. Yeah.
Johannes?
Sound, but I think it's what we're looking at. You have the market expectations for both the rates and the inflation. You can essentially construct, I think, before what the market thinks the reaction function is.
Right.
Some measure.
Yeah.
And then essentially, they try to decompose the surprise into like, okay, this is the provision of the inflation model.
Right. Yeah. So we've been thinking about kind of expanding, and we've been working on expanding the theory to think about essentially there's two types of learning going on, both the learning about the information and then also using that information to learn about the reaction function. Okay. And so we could, do exactly what you said, is essentially back out what the effective surprise is relative to the rule, relative to the information, using that information. So that's certainly something we're doing, and hope to have a better sense of.
Okay, so have you looked at if SCP meetings are different in like some other way other than just this information? Like, is the language used in the meeting like more consistent with forward guidance, or are they using more words in their
Right.
like
So,
in their press conference or in their statement?
So the concern, of course, would be if the FOMC statement, because we're only looking around the 30-minute around the statement. So the concern would be, is the wording in the statement systematically different for SCP meetings or non-SCP meetings? And is that in some way correlated with this information? So there are papers that have looked at kind of how statements have evolved. We haven't looked at that directly, but I haven't seen the fact that these statements, or particularly for following these, these statements aren't changing, and they're typically not referring to the SCP in the statements themselves. But that's certainly a valid point.
Once you actually say a bit more about the last bullet.
Yeah. So what we do is we go and run these kind of local projection type regressions, and it has all the concerns that you have. We're looking at a fairly short sample, but the key point here is these different types of shocks. So the red line is the raw surprise. The blue line is just the orthogonalized with respect to information, and the blue line is pulling out the information. And it's really, you're seeing a clear, these are all normalized to a 25 basis point increase. And what you're seeing is a clear discrepancy here, and larger effect on the excess bond premium, and then less of this kind of inflation price puzzle going on. So, there's a lot of uncertainty, so relatively small samples, so you have to take all this with a grain of salt, but at least what we're seeing is kind of consistent with what you would expect from a kind of an information effect.
Price for the expected fund rate year ahead.
Correct.
But you're not controlling. You're controlling for the target rate of price, but not the expected policy rate of price. Seems like that's the one to control for you. You really want to isolate pure macroeconomic information.
Okay. So, I mean, we're using this. So I have to double check on that, but we're using all of the information in terms of the forecasts that the survey is using. And that is identical to the information that what the SEP is producing. So we're kind of using everything, at least, but I may be missing something, so I'm happy to chat with you after.
Sort of a broader interest question. The SCP is probably under debate right now.
Right.
Does this paper, move you in some direction as to, inform that debate in some way in terms of, the value of the SCP or?
I mean, I think, so Tara and I have had a lot of discussions about this. We're certainly looking at further work that kind of tries to get at that in more detail. I think, the way I think about this paper, it tells you to some extent the frequency of the releases, right? So to the extent that you're getting larger surprises with these information release, if you were to release it more often, you could potentially, we would expect those information releases would be smaller, right? Because you're basically giving the private sector less time to kind of drift away from the Fed's expectations, right? So that's kind of the best we are thinking about with now. We have other thoughts, but I think we're going to save that for kind of future work.
All right, let's give them another round of applause.
Thank you.
And on to our last presenter of the day, which is Laura.
Good. Thanks for having us, for putting the paper in the program. This is joint work with Miguel Bandera, who's at NBER and located over there, ready for the hard questions, and Sean Wan, who's somewhere in the room. He's over there, grad student from the University of Minnesota. Let me start with some very general motivation. The surge and retreat of post-COVID inflation has more recently renewed interest in nonlinear dynamics of price adjustment. Obviously, in tackling this question, the most natural framework tends to be manual cost models, because those are models where firms tolerate some degree of price misalignment because they're facing these adjustment costs. And therefore, how many of them tend to adjust following a shock is an endogenous object. And this is going to give rise to nonlinearity, state dependence, and so on. Most of the focus of the literature that has been targeting this question has been focusing on a particular dimension of the nonlinearity. There's people in the room that has been working on this, and has to do with the size of shocks. The idea being that bigger shocks are going to move disproportionately more firms to adjust. One way in which you can represent this idea with some caveats, of course, but just graphically, is by plotting the distribution of price gaps, where the price gap is essentially capturing how far the price of a firm is relative to the price it would set if it was actually going to readjust. The reason that this distribution of price gaps is useful in explaining shocks is because in these models, price adjustments are infrequent. So what tends to happen is that the price gap tends to drift together with inflation, nothing happening up until it kind of crosses the threshold here represented by the S lower bar and the vertical dash line. And after that, the threshold crosses that line, we see some readjustment happening. So all we need to understand, or most of what we need to understand, is how the shock is going to affect the number of firms that are going to be crossing that threshold. So the idea is if you have a small shock, like you can see in your left-hand side, there's going to be a smaller shift in the distribution. So there's going to be a few number of firms that are going to be adjusting. The change in the price is not going to be that big. That's like the shaded area in blue. When you have a big shock, like the one to your right, the displacement is going to be much bigger, and that's going to lead to this disproportionately bigger share of firms that are going to adjust, and therefore price levels are going to see a bigger jump. But just by looking at this, it comes across pretty naturally that when you want to think about the effect of shocks on the share of firms that adjust, it doesn't only matter how big the shock is, but also the distribution at which the shock hits. So it's very easy to come up with examples where you still have the same shock, but the shock is arriving at a point in time where the distribution is already tilted towards the threshold, and therefore the same shock is going to generate a bigger share of firms adjusting, and therefore some nonlinearity in the response to the shock. So the takeaway from here that I hope you take is that when we think about the inflation response to shocks in menu cost model, it's not only about the size of the shock, but also the distribution at which the shock hits when the shock arrives. And that's exactly what we're going to try to kind of focus this paper about in the distribution of price gaps. We're going to try to kind of re-emphasize its role in menu cost models theoretically. This is not going to be new. Anyone that has worked with this kind of models will kind of very quickly say, well, this is a state variable. That's really what we're saying. But more challenging is to go to the data and try to recover those price gaps empirically and see whether they change over time, and use the variation that we're going to see over time to kind of test to what extent this price gap distribution actually shapes the inflation dynamics in the data. So the paper is going to be divided into 3 different parts or sections. The first one is going to be pretty theoretical. We're just going to go back to a very standard random menu cost model. Think about Nakamura and Steinson 2010. And we're just going to bring back the gap distribution to the center of an analysis. As I was saying earlier, this is pretty trivial if you work with these models. All we're saying is that the gap distribution is going to be the key state variable in the model. But having the model is going to help us do 2 things. One is just going to be formalize the intuition that I put early on as the motivation. We're going to be able to show that in numerically simulated version of the model, that if you look at the propagation of shocks hitting the same economy, the same size, but at different points in time, thinking about the history that the economy has been suffering, that's going to lead to very different responses of the economy to the same shock. Obviously, this is going to have some implications for optimal policy that are kind of going to be, we're going to leave for future research. Also, if you want to think, in the absence of shocks, or at least unconditionally, the same intuition as to why the distribution is going to lead to different propagation of shocks is also going to help us understand that it's a kind of a leading indicator of inflation. The idea being that the distribution is going to be containing all the pending adjustments that over time are going to be panning out. Therefore, we can tell what's going to happen with inflation by looking at what the distribution is today. This is a result that we can show analytically in the basic model. In the interest of time, I'm not going to go through the model contribution. Encourage whoever's interested to read the paper. I'm going to go directly into how to handle this empirically, because this gap distribution is an object that we cannot observe directly from the data. So the second part of the paper, and the main contribution, is going to be the methodology. We're going to try to recover price caps empirically by just looking at realizations of actual prices. This methodology has 2 different steps. The first one is really easy. It's just to recast the random menu cost in state space form. And by state space form, it simply means, we're going to have a set of observable variables, the prices. We're going to have a set of unobservable variables, or hidden states, the reset prices, and because it's a Calvo plus model, the arrival of readjustment opportunities. The unobserved variables are going to have a law of motion that are going to be given by the model, and all I'm missing is going to be a measurement equation, which is mapping the hidden states to the observed variables. That's really what I mean by just rewriting this in a different way. Once we've rewritten it in state space form, we can develop state space methods to estimate the parameters of these models. And here I mean the parameters that rule the relationships between the hidden states and the law of motions of the hidden states, but also the latent or hidden states. So the actual reset prices, so we can construct ultimately the price gaps. One takeaway, I'll go into the details on how we do this more specifically, but if there's one thing that I want you to take away with you and how we do it is we're basically going to exploit the structural optimal policy rule that comes from the menu cost models, the so-called SS rules. We're going to kind of very much leverage on the boundedness that that's going to provide us to do the filtering, but also the variation estimation of a lot of the parameters. Then finally, the third part is it's obviously an application. We're going to take our methodology to the data. We're going to be using UK CPI microdata that spans over 30 years, starting 1996. And we're going to estimate price gaps for million of quote lines over this period. What do we find here? What do we think is cool here is, first thing, the gap distribution changes a lot over time, and it changes in ways that headline inflation is going to be hiding. So there's some additional value in kind of estimating the gap distribution, and we're going to exploit this variation or this fact that we see things moving around in two different dimensions. First one is we're going to look at state-dependent shock propagation. So going back to my argument on why is it important in the actual model, we're going to see that if you have a monetary policy shock, it's going to transmit to prices very differently depending on the time where the shock hits. And in terms of quantitative, it can be twice as effective in moving prices. Again, unconditionally say that we're not so much concerned about shocks as of now. We can see this idea of a leading indicator of inflation. We can test that the distribution is actually a predictor of actual inflation, and it actually does better than some of the benchmarks in the literature. So we can quantify the gain when it comes to inflation forecasting. And with that, I'm going to start in with the second contribution directly. Let me just build the set of assumptions that I need from a very simple random menu cost model. This is going to be obviously reduced form. Micro foundations are in the paper. You can read Emmy's and John's paper. Also, Ludwig's papers. We're kind of building very much on the micro foundations they have over there. I'm just going to lay the ingredients that we need today. We can complicate things much more. So we're thinking about a firm that's setting the log price in discrete time. It's going to be facing some adjustment cost. That adjustment cost can collapse to zero with some probability lambda. That's going to be the time dependence or Calvinus. And with the 1 minus lambda probability, it's going to be some positive fixed menu cost. The firm is going to care about its price and its reset price, which is the price that it would choose in the event of adjustment. We're going to assume that follows a random walk with drift. So it's kind of subject to idiosyncratic shocks. And in the model, we're not going to allow for aggregate uncertainty, but we want to talk about shocks. So the kind of shocks that we have in mind are going to be MIT or unexpected shocks. What moves around? Most of the time we think in these models about shocks to the trend inflation component, because we're going to let the data speak. We're going to be very agnostic. We're going to allow for shocks to the idiosyncratic shocks that might be more related to the COVID episode, depending who you ask, and also on the arrival of the free adjustment opportunities. So in this kind of models, as many people have shown, it's pretty useful to write the firm's problem in terms of the price gap. So this is kind of the element that we're going to be estimating, which is the difference between the price and the reset price. And the firm is essentially going to set prices to minimize the loss associated to not having the price gap equal to zero, meaning that you're deviating from what you want it to do, plus the cost of paying for the adjustment in case you choose to do so. And the optimal pricing rule that comes from this problem is what we normally call an SS rule, meaning that the price gap is going to be set to zero in the event of an adjustment. That's going to happen with some probability lambda. If you have a free adjustment opportunity, you choose to adjust. Or if you don't have a free adjustment opportunity, but the previous price gap is kind of drifting outside what we know as an inaction region, which is going to be bounded by an upper threshold and a lower threshold, the lower of which I was showing in the motivating graph. In the event that there is no adjustment, what's going to happen is we're going to allow the price gap to move passively. It's going to drift away with inflation, and it's going to also be subject to the idiosyncratic shocks. So in this kind of models, the assumption is that the policy parameters, the bands most specifically, are common across firms. So the aggregation is very neat and transparent. And when we think about the inflation dynamics or any sort of aggregate dynamics in this model, the key state variable is going to be the price gap distribution, which of course is going to be bounded by the bands, and it's going to be peaking. There's going to be centered at the price gap equal to 0. So this is going to be the object of study. This is what we want to try to get from the data. Traditionally, when you think about structural models, the way we do this is we look at a stationary distribution. We pick a bunch of parameters for a bunch of moments from the microprice data, and we kind of calibrate the stationary distribution around that. We want to allow that to be time varying, and that's what's going to force us to do this more empirically and use especially a bigger set of data, not only a couple of moments. So let me just run you through how to rewrite this model, which most of you, if not everyone, knows, into a state space representation. We just have to tweak a couple of things. As I was mentioning early on, what are our observables in the data? We can see prices. And because we can see prices in a panel, we can also see when the price change happens. So we're going to kind of code that as an inaction indicator that's going to be equal to 1 if there's no price change. What are we after? What are the hidden states? The hidden state that we need, the most important one, is going to be the reset price. That's what's going to allow us to estimate the price gap, but also the free adjustment opportunity. That's going to be important for the process. We don't know whether you're changing your price because you were kind of touched by the Calvo fairy, or instead because you're paying the menu cost. So these two set of variables are kind of related to each other through the measurement equations. And the measurement equation is just a different way of writing the SS rule. There's nothing new here. We know that the price can take two values. If there is inaction, it's going to stay as it was, PIT minus 1. If instead we see a price change, if DIT is 0, we're going to see it become the reset price. The inaction dummy is also going to have this formulation where inactivity is going to happen if you don't receive a free adjustment opportunity, if the L here is equal to 0, but then your gap lies within the inaction region, then why would you change it? And there's also, for completeness, a possibility where you do receive a free adjustment opportunity, but you're exactly at the point where you want it to be. So then you're not, there's no price adjustment that we observe. When we take this to the data, the mass here is going to be 0. And then the hidden states are going to have some evolution, some transition equation that's directly coming from the data. So this is from the model. This is just a repetition from the previous slide. The reset price is going to have this random walk with drift process, and the free adjustment is going to be a Poisson process with probability lambda. What are the parameters? We're grouping together a combination of structural parameters in the microfoundation, so those that run the stochastic process, and then we have the reduced form parameters that are coming from the optimal policy, the inaction thresholds. Together with some initial conditions for initial values for the hidden states, we have put together a state space representation of the menu cost very simply. How do we estimate the parameters and the hidden states jointly? There was a question, right?
Yes. On the inaction thresholds, are you assuming that the price setters choose the inaction thresholds optimally given the mu-t process? Or their process for
so we're assuming,
or are you saying however they come about, we're going to back them out from the data?
We're going to back them out from the data. We're going to kind of average over time with the MIT shock.
Perfect.
But that's coming a little bit later. So how do we do the estimation? So a couple of things. This representation is for a single eye. We obviously have a panel of observations. So just to extend it to the state space representation, we need to make some assumption about the commonality of the parameters. Based on the model, we assume that it's common throughout the estimation stage. Just to kind of anticipate a question that comes very often here, we're going to be the unit of observation when we take to the data, it's going to be the quote level, right? So think about a product being sold at a specific location. We're going to do the estimation at the item level, meaning that we're assuming that the parameters are constant within an item level. So it's very kind of disaggregated. The other thing, I think back to where Ludwig is going, is we need to make an assumption on the parameters. We're going to think about estimation windows, which are really going to be really small. And then within that estimation window, item level, time specific, the set of parameters is going to be constant, but we're going to allow them to vary over time. So we're going to see some movement, but not the whole movement that we would love to see. So what we're going to do is use the data to estimate the parameters on the hidden states using a Gibbs sampler. A Gibbs sampler, as you probably know, is this an iterating process where you're going to be sampling one unobservable variable, holding the data and holding the other unobservables data constant. So we're going to split it into two different blocks. The first one is probably the most interesting, is how do we get around the hidden states? So we're going to sample hidden states conditional on parameters. This is essentially a two-step procedure. We're going to do forward filtering, where we're basically updating our beliefs about what the hidden state is as we keep on receiving the data based on the prices. And a forward filter, like you remember, is just basically we're going to be projecting your hidden state in t-1 using the transition equation from the model, and then we're going to update that prediction based on what we get from the data. That's just a one-sided estimation, only uses information up until period t. If we want to use, and this depends on the exercise, if we want to use the full information, we're going to incorporate a backward sampling step that's going to go the opposite direction, but they're kind of going to be very similar in terms of the intuition. What is the complexity that we have over here? The first problem is that this is a very nonlinear model. Like this SS model has kinks, and that's going to rule out any closed form solutions for the recursions that you're going to have in the forward filtering problem. So we're going to have some numerical approximations on the integrals that enter the forward filtering problem, and that's going to require us to discretize the state space. So what we want to do is we want to use the SS rules to guide us on how to narrow the state space. And kind of the key thing here is that the measurement equation, the SS rule, is deterministic. So given the parameters, we know exactly which hidden states are consistent with the data that we're observing. Let me give you some examples. Suppose that we observe a price change. If we observe a price change, we know exactly what the reset price is because we're setting the price gap equal to 0. Also, if the price change is small enough, conditional on the parameters, we also know that that was a free adjustment opportunity, that the change comes within the bands. If the price change is large, well, in that case, we don't know whether it's a free adjustment opportunity or not, but we're kind of up to these 2 degrees of freedom. Finally, if we don't have a price change, which is the worst case scenario, we at least know it was not a free adjustment opportunity, but we don't really know where the reset is. The measurement equation, the SS rule, is going to bound where the reset price can actually be. So we're going to be, given that we're kind of restricting where the state space can lie, we're going to be able to construct time-varying grids and weights for these latent states. This is going to speed up massively the filtering. It's going to also ensure accuracy, especially given that we're going to do this filtering at the quote level. So we're going to have millions and millions of filtering processes.
Sorry, can I ask, like, suppose you had a model where instead of the like SS, the bounds were like constants, you assumed that they were random, like, you know, the cost of changing prices were somewhat random. So then that would become a latent state variable.
Yes.
Wouldn't that like smooth out your problem in various ways?
It has their function that's a little bit smoother.
And would that help you computationally or hurt you computationally?
So that's a good question that Ludwig has asked in the past, which we've started exploring, but we're still kind of unsure. Miguel, do you want?
It might help, but we started with the difficult one. We solved the difficult one. That's the honest answer. But we're.
But it's on our to-do list, yeah. The second block is the opposite round, right? Once that we know the hidden states, or we control for the hidden states, how do we sample the parameters? For like the 3 stochastic processes, we're going to have conjugate priors, closed form solutions, very quick step. Again, we're going to have to use the SS rules for the inaction thresholds. There's a metropolis hastings that's going to be over here. The beauty here of again having a measurement equation that is deterministic means that the the proposed, the candidate values for the bands, the likelihood is going to be either 0 or 1. So your candidate values are consistent or not with the data. There's no uncertainty over there. So you can build proposals where you only have candidate values that are consistent with the data. So again, that's going to speed up a little bit more. We're going to alternate between the blocks for a number of iterations. And as it's standard, once that you propose a methodology, we're going to have a Monte Carlo that's going to prove that, or it's going to show that we're able to recover parameters and gaps with negligible bias, even if the sample is finite and even if the sample is small. And with that, let me go to the data. Let's bring this algorithm and apply it to some microprice data. So we're going to use the microprice data underlying the CPI in the UK. That is the universe of locally collected prices. That's around 60% of the prices that go into the CPI in the UK. We cover around 140 locations, and the data spans over 30 years up until January this year. That means that we have more than 35 million quotes in quote lines, which is our unit of observations. That's 3.6 million. And we're going to have around 1,300 items. That's going to be the estimation level that we're going to be doing. So a lot of people have used this data set before, so we're just going to follow their cleaning procedures. That means dropping sales, dropping product substitutions. The one thing that we have to be very careful because of the filtering is what to do with broken quote lines, and we kind of basically split them so that they're two independent quote lines. As I've mentioned already, the unit of my eye here, taking the model to the data, my eye is going to be the quote line, and we're going to repeat the estimation for every item separately. Estimation windows. We're going to start with the calendar years because that's where the product substitution happens. And then what we're going to do is we're going to keep it as short as possible, but extend them so that we have at least 10 positive and 10 negative price changes. That's what's going to allow us to identify the bands. That's kind of the trade-off that we're going to be facing. Turns out that almost all, like 90% of the item windows span exactly 12 months. Do you want to see like confusion? Okay, then we're going to be aggregating stuff up from the item level up to the CPI or the economy level, and we're going to be using official weights over there. So parameters, the first step was estimating parameters. In the interest of time, I've spare you from like looking at the table. It's in the paper. We have some summary statistics for all the posterior means. They're very reasonable and they fall very much in line with what has been found with the literature, which kind of brings some comfort given that we're doing things in a very different way when it comes to the estimation. Once that we have the parameters and we've kind of recovered the latent states from the reset prices, and we can construct price gaps, then we can kind of aggregate things up into an economy-wide price gap distribution. And this is what we're plotting over here. We're going to plotting a couple of moments of that that we think are useful to kind of gauge like what's going on. We have the median in gray, and we have two set of bands, which are the interquartile range and the 95% percentile. And then on your right axis, you have year-on-year published headline inflation. So remember, we're doing part of the microprice data that goes. We're kind of showing you, we're making our life a little bit more complicated by looking at the actual published figure. What we kind of make out of this figure is that there is a lot more variation in the moments that describe the distribution than there is in actual inflation. Inflation kind of moves from minus 0.1 in like 2014 up until 11% during COVID. But if you look at especially the dispersion measures, they move something between 2 to 30 percentage points in case of the interquartile range. When it goes to the 595 range, it's something like 33 to 86. So there's a lot of variation that's kind of picked up by the dispersion measures. Also, if you're willing to eyeball, and I'm asking a lot over here, so I'll do things more formally, but if you're ready to eyeball, there's also a lot of changes on the side of the distribution that's kind of more populated. Emmy?
I was trying to look for skewness during the COVID inflation surge. There's this paper by Ball and Mankiw about the notion that, skewness might be an important moment.
That's price changes, right?
For price changes, but one has the sense that, with cost push shocks or, with like commodity shocks or something that, and there was a lot of the discussion in the COVID inflation surge, it's all coming from used cars or oil prices or something. But it's not obvious, something like that from that picture. Anyway, have you investigated that kind of question?
So we're going to go through, like when I move forward, we're going to go through like the 4 moments that are going to be key, which is like the 4 first one of the gap distribution, not the price changes. Those are different. We find, this is not on the paper yet, and it's like, but offline, we find that things during COVID are very similar. Where it's very different is right now, which we think it's like really interesting. There was a question back there.
So I was just wondering about whether this is sort of graphing the same thing in the sense that CPI inflation is including lots of stuff that you're not measuring the price caps for. Is that correct? So how much of the CPI are you covering?
60%.
So 60% of items or 60% of the expenditure weight?
60% of expenditure weight.
Okay. So the CPI in the UK, in the US, like 45% is housing alone. So is it different?
Rent is not here because that is centrally collected. But there's some additional stuff than what you would have in the US in terms of services. In the headline measure.
Can you remind me, so the parameters of the model, are they being held constant over time, or?
They're held constant over this estimation windows, which they tend to be like around 1 year.
Because, the median, like, it's like 0, almost exactly until 2009, and then it drifts very persistently away from 0. And I'm wondering if this has to do with some shift in distributions that your model is not allowing for, or something like that, like a variance getting bigger or something.
So we're going to have the volatility of shocks changing over time as well. So that's speaking. We don't have a story yet because like the plots for the time varying parameters is one of the things that we don't have here. It's like, how can that tell a story of what might be going? But we are allowing for that to change over time, it's very important for kind of the message that we want to get across. Okay, so let me, zoom into, the idea is that there's a lot of variation. There's variation in the dispersion, but there's also variation in which side of the tails is going to be kind of more loaded. Let me zoom in 3 different dates to kind of give you the idea of the mechanism that we have in mind. This is in the form of case studies. I'm going to look at 3 different dates, and these are going to be 12 months before 3 important inflationary outcomes. I'm looking at September 2007, which is 12 months before the pre-COVID inflation peak. So that's like the largest inflation rate in the UK before the COVID inflation episode. We're going to look at April 2014, which is the lowest level of inflation in the sample. And then we're going to look at the 12 months before the actual COVID peak. And we're going to compare those 3 dates with some measure of what an ergodic distribution would be. And the way we're going to do that is we're going to look at the long run average of the moments, and we're going to find the date that is closest to that long run average. That turns out to be March 2024. And actually, if you look at the inflation that follows that March 2024, turns out that it's 2.6%. That's very much in line with a sample average of 2.5. So that's going to give us some confidence that it is something reasonable in terms of an ergodic distribution. That just to be able to compare, to have some comparison. So September 2007, the economy is going at, inflation is something like 1.7. We're going to be plotting the price gap distribution. You have the PDF, the kernel density. You're going to have the CDF. Choose the one that's more natural for you to read. We have like differing opinions among co-authors. That's why you have both. In gray, you're going to have so the shaded one is going to be the benchmark, and then the other one is kind of how it's moved. What we see is that in September 2007, the distribution shifted towards the left. meaning that there is some inflationary pressure building. And actually, if you look at what happened to inflation later on, that's the last figure to your right, you see that inflation 12 months actually peaked at 5.1 in the pre-COVID. And that's like almost double the benchmark that's plotted in the gray. April 2014 is going to be the mirror image. This is again a period where inflation is at 1.8, so the difference is very minor if you're looking at headline inflation, but the distribution looks very different. In this case, what we find relative to our measure of ergodic is that the distribution is kind of shifted towards the right, so you're going to have a lot of firms that want to cut their prices. Again, if you look at what happened to inflation during those 12 months following the date, you see that there's little movement. If anything, there's a decline compared to the stationary or the long run average. There's a clear deflation relative to the 2.5%. The third case, probably the most exciting, is just before COVID. Here, things are a little bit different in two dimensions. First of all, we already have a little bit of inflation. There's 4% in October 2021. And more importantly, the distribution of prices, the distribution is two-sided. We have both tails being pretty thick. So it's kind of unclear from here what direction it's going to go. We obviously know with the benefit of hindsight that the Ukrainian war happened, there was an increase in oil prices, and that ended up generating this increase in inflation, reaching the peak at 11%. This is kind of a very useful example as to what is the limitation of a case study, meaning that we know that there is kind of accumulation in the tails, but it's really going to depend on what tail is being hit. So we're going to try to make some progress in disentangling what is the role of the distribution versus what is the role to the shock by looking at identified aggregate shocks and seeing how they propagate differently across different economies. So price gaps and shock propagation. So we're going to do a relatively standard local projection model where we're going to add this state dependence based on the distribution. So we're going to do this at one level of aggregation beyond items. So this is a COICOP class. And we're going to kind of project the log of the published price index for that specific class, H periods in advance. Our shock is going to be a change in the 1 year gilt yield. And we're going to have the standard set of controls in a standard local projection. What's going to be different is we're now going to have the interaction of the shock with standardized measures of the moments 1 period before, moments of the price distribution 1 period before. And we're looking at how does this coefficients play out and especially whether they're significant. Because the kind of the mechanism that we have in mind is directional. For the moments that are odd, we're going to basically the mean and the skewness, we're going to allow them to enter sign independently. So there's going to be different reactions for tightening and for easing. And in terms of identification, we're just going to build on the literature of high frequency shocks and borrow the target. We're going to instrument both the shocks and the interaction of the shock with the moments using the target path and quantitative easing shocks from Brown et al. For the talk today, I kind of chose to do monetary policy shocks because that's what most of the literature has been focusing on. That's the shock to the trend inflation that we have in the model. But there's an alternative set of tests where instead of looking at monetary shocks, we look at oil price shocks using the OCAN6 job market paper identification strategy. So the first set of results, we've tried to condense everything in a table, which is relatively non-standard for local projections, but I wanted to show you what is the horizon effects and what are the different regressors. So in the first row, all you see is that when there is a tightening, prices are going to go down and it's going to be accumulating over time. So your standard impulse response to a monetary shock. Then we're kind of adding simultaneously each of the different moments of the distribution. I mean, that goes back to some of the questions that we had early on. Most of the state dependence is going to come from the mean, and it's going to go in the direction that we were kind of speculating when looking at the case studies. It's going to the shock is going to be amplified when it's pushing towards the direction where the mass of the distribution has been concentrating. So in the case of tightening, that's going to push the price down. The more mass we have to your right, meaning there's more kind of firms wanting to cut prices, the more effective that tightening is going to be. It's also pretty the standard deviation is also going to be pretty important, and that's going to speak to how you know, the bigger the standard deviation, the thicker the tails, and that's going to amplify the shocks in both directions. There's a little bit of stuff going on in the skewness and the kurtosis, but once you account for the mean and the standard deviation, that's mostly where the state dependence is going to show up. There is some evidence as well on if looking at the F-stat for significance, joint significance of the interactions for most of the horizons. But these tables are always really hard to interpret. So let me give you impulse responses to these monetary shocks. These are 25 basis points monetary shocks, using the two examples for the state of the economy that I was, well, one of the examples I was using in the case studies. I'm going to be focusing on October 21 because that was the most interesting, with the two tails being very thick. So it's going to work in both directions. You can find all the other examples in the paper. So what do we get here? We get the black line is going to be the impulse response for October 21. And we're going to compare it to our measure of a benchmark in March 2024. We see that, you know, some tightening is going to lower prices, whereas some easing is going to increase prices. And in both cases, the transmission of the shock to the price level is going to be amplified into October 21 relative to our benchmark. This difference in the response is statistically significant across all horizons. And if we want to get a sense of how big this is, for, you know, like looking at different horizons, but if you look at, like, you know, 6 months in for tightening, it's something like 25%. It's 1 versus a 0.8. It's a little bit stronger when you look at the easing. It's actually around 50% higher. But of course, we can do this every single month. And by doing that, what we can come up with is some index of monetary policy pass-through that kind of varies over time. And this is what I'm showing over here. So this is the response of inflation to monetary policy tightening after 12 months. So the H is equal to 12. And I'm going to compare that response to the response that we would have in the benchmark economy. So that's March 2024. And what we see is that there's a lot of variation, and the variation ranges from being twice as effective, or at least the transmission, depending on how you read effective, of course, the transmission to prices is twice as big in kind of the extreme. It can actually fall to 0, and in some cases even deliver a price bustle in other periods. Of course, this is for hikes. It works similarly for monetary easing. Let me just emphasize that it's not the flip side, because the mechanism is directional. It's not like one side versus the other. It's how much it accumulates close to the threshold relative to the other. Okay. Up until now, everything I've said was either conditional on 3 dates or conditional on the shocks. But we can move a little bit further and try to see whether we do have some evidence that there is some kind of adjustments that are accumulating, that are picked up by the distribution, that would eventually be released and therefore offer some predictive content of inflation through the price gaps. So we're going to do this in 2 steps. The first one is just a straight question: does the distribution predict inflation? We've proved this in the model. Can we see it in the data? And for this, we're going to run a panel VAR with 12 lags, and we're going to test for causality in both directions between year-on-year inflation and moments of the gap distribution. The results show that it's one directional. So we do see that lagged gap moments are going to predict inflation, or going to help predict inflation, but the other way around doesn't hold. And then the more important question is, okay, there is an increase in forecasting, or like in the predictive power, but by how much? And the second thing we're going to do is some sort of quantification to see how far do we get. So a couple of things to mention here. Here we're going to use real-time moments of the price gap distribution, meaning we're not going to use the information ahead, because to some extent that would be kind of cheating. We're going to use this real-time measure so that you could kind of export it if you were to do this in real time. We're going to kind of fit a year-on-year inflation forecasting regression on the moments. We're going to estimate the coefficients between 1996 and 2016, and then we're going to evaluate the forecast performance out of sample. To get some benchmark as to what is reasonable in terms of improvement, we're just going to use the framework, the standard random walk benchmark by Atkinson and Hayan, which is surprisingly hard to beat. And we're going to be, I've presented here the results as a ratio of the error of our model relative to the error that you would get with a simple random walk. So anything below 1 means that we're doing better than the random walk scenario. What we see if you look at the full sample is that in all cases, it's smaller than 1. It's significant for longer horizons, and it's actually increasing in terms of how much better we do, up to the point that we reduce errors 28% after 2 years. If you split low inflation and high inflation, because COVID was particularly difficult to forecast, you do much better. You're going to reduce the error 50% after 2 years. And let me just conclude with 2 different things. The first one is like a summary of the takeaways from the talk today. The paper is about kind of reivindicating the price gap distribution as the key state of menu cost models. This has been a constant in some of the SS frameworks. It's not new. What we're bringing to the table is a way to take it to the data in the pricing setup, in the pricing framework, by using state space methods that are going to recover the price gaps from observable prices. So we need the data that's available for most of the work that has been done in microprice data. We apply it in the UK over 30 years, and we see that the economy does spend time outside its zaccordic or long-run average. And some of the information that this variation is producing is going to be helpful in quantifying empirically how distribution matters for inflation dynamics in 2 ways. There's propagation, same shock, different effects depending on when they hit, and then prediction, if you want to think about unconditional statements. In terms of looking ahead, and that's where I'm gonna close the talk today, there's 2 things that we find exciting. One is, if you trust that the propagation of shocks depends on the distribution, then there is a case for how optimal policy should kind of think about rules that account for the distribution at every point in time. And then more generally, the method is very generalizable. We are using this for the very simple random menu cost model. We can add more layers of complexity, maybe also some layers of simplicity, thinking about John's point. And of course, it could go very well beyond pricing. We have some interesting work coming up in terms of investment. And with that, I'll conclude. Thank you.
So in terms of prediction, your paper is in some sense quite related to this other recent paper by Zhou Hazel and Chen Lian and co-authors.
Which they're presenting on Friday, I think.
Yeah.
I don't
And so, I mean, that paper uses totally different methods and in various ways very different, but I don't know if you have any thoughts on
Not yet, because we haven't been able to find the draft.
Oh.
So we looked at it.
Yeah.
So I'm excited about seeing it.
Jen is my colleague, so I've seen the paper, but okay, that's unfair.
Great presentation. I have 3 short comments. First, you had a bullet on the slide where you said Monte Carlo or verification. Was that you kind of drawing data
So that
from
is-
an actual model and then verifying you back out?
Exactly.
Perfect. Second is just following up on the smooth adjustment hazard that John mentioned. I think it's very easy to apply the sort of Alvarez-Lippi-Oskolkov method.
Yes.
And you could just do that in your sort of 1-year interval.
1 year.
See what does it look like? How does it compare? I think that'd be very interesting. And third, on the empirical exercise, I think monetary policy is super interesting. But it would also be interesting in your context to try to go a little bit more granular, right? If you have
Okay.
sort of category specific shocks, you mentioned oil price shocks. I could think of other food price, other commodities that could move around. Because then it gives you a little bit more variation and it's not just kind of mostly coming off the time series.
Okay, that's what point well taken now. Johannes?
Yeah. One question. Like, you can also look at whether how the predictions look in the cross section, right? So rather than just in the time series. And the second question I had is, the model, I think, makes some predictions for what moments of the G distribution should be important. But I think you let the data speak there, and it'd be useful to see what the data says compares to what the model says.
So we do well for the moments that the type of model we're estimating use for the calibration. For some of the discussions on you should be looking at other moments, we're going to have the exact same problems that those papers initially have. So we have nothing to say on that discussion. For the standard ones, meaning like, so for the, let me put it this way, for the theoretical results for the simulations, we basically calibrate the model in the standard way. For the moments that we use for that calibration, which is, the Neckermann-Steins and so on, for those, we like there is a perfect fit. Some of the others, start thinking about kurtosis, there is a little bit of tension over there, but it's because of the model we're using. If you give me a different model, we can estimate it, we'll do better.
You said that 2026 looks different. I was wondering if you could say a few words about that.
So Ricardo Rice gave a talk the other day, like a week ago, where he did talk about this. We had some of the plots generated for him. Like, well, if I remember correctly, Miguel, you were the one that delivered this. What we found is that in January 2026, the economy was prone to an amplification of an oil price shock. And it's also the time where the monetary policy shock is less effective. So I think some of his takeaways were in that direction.
26, there's a lot of a left.
There's a lot,
There's a lot of a left.
So if you look at some of the price change moments, those would say that we're back to steady state. Our price gap distribution says that we're kind of very loaded on the left side. We cannot go beyond January because the ONS has changed the way the data is collected. So unfortunately, that's gonna.
So can you comment on the intuition for why the price change stuff looks like it's back to steady state, but the price gap distribution looks so different? What's how do I think about that?
So we don't have a story there yet. It's true that we haven't looked at the price. This is like his work.
Sure.
So we haven't looked at the order sum. I mean, it's the same data. So we would be very surprised if it's
Just
different.
before, the gap should build, maybe you still don't see it in the moments, but you see it in the
You're
gaps.
seeing it. It's like
Eventually later, these things are gonna be released, maybe the moments would tell, but if you do this in real time up to 26, the gap is showing a left tail that hasn't yet materialized into pricing moments into that, up until that data.
But we're not going to be able to verify because the data is not going to be available after January 26th. That's the, because it's, they've changed the way some of the data is collected. So there's going to be some gap there on which we might need to figure out how to fix. But up until now, it's like January 26th is our cutting point.
Okay, let's adjourn. So, I was thinking like, obviously I was. I was thinking, so like, how should I use it as a practical monitor? One perspective is what's appropriate.
Researcher.